In the vast expanse of space, where light travels for billions of years to reach our eyes, there exist regions so dark, so dense, and so mysterious that they challenge everything we thought we knew about reality itself. These are places where time slows to a crawl, where space itself is torn and twisted beyond recognition, and where the very laws of physics break down into chaos. They are called black holes. Welcome to Aether Theory, and tonight we're going to venture as close as science will allow us to these cosmic monsters that lurk in the darkness between the stars. Imagine, if you will, standing at the edge of infinity. Before you stretches a sphere of absolute nothingness, not empty space, but a region where space itself has been so violently distorted that it forms a one-way tunnel to, well, that's exactly what we're here to find out. Because despite decades of research, despite revolutionary discoveries, and despite having now actually photographed these impossible objects, black holes remain one of the universe's most jealously guarded secrets. What you're about to hear may fundamentally change how you see the cosmos. We'll journey from the violent deaths of stars to the gentle warping of space-time. We'll explore how these invisible predators shape entire galaxies, and we'll confront the mind-bending possibility that every black hole might contain an entire universe within it. But be warned, once you truly understand what a black hole is, you'll never look at the night sky the same way again. Because scattered throughout the darkness above us are millions of these cosmic graveyards, each one a testament to the universe's capacity for both creation and destruction. Let's begin our journey not with complex mathematics or abstract theories, but with a simple question that haunted scientists for centuries: what happens when gravity wins? Picture our sun, that magnificent ball of nuclear fire that has faithfully provided light and warmth to Earth for over 4.5 billion years. Now imagine that same sun compressed down to the size of a city, then compress it further down to the size of a mountain. Keep going down to the size of a building, a car, a marble. At what point does something extraordinary happen? At what point does matter become so dense that not even light itself can escape its gravitational pull? The answer, as we'll discover, depends on a delicate balance between forces that have been waging war since the very birth of the universe. It's a cosmic game of tug-of-war between the outward pressure of energy and the inward crush of gravity. And in this game, gravity doesn't just win, it achieves total, absolute victory. But here's what makes black holes truly terrifying. They're not just theoretical curiosities confined to the pages of scientific journals. They're real. They're out there, and they're feeding. Right now, as you listen to these words, there's a supermassive black hole at the center of our own galaxy, weighing as much as 4 million of our suns, slowly consuming everything that ventures too close. We call it Sagittarius A star, and it sits roughly 26,000 light-years from Earth, close enough that we can actually watch stars orbit around its invisible presence like cosmic moths drawn to a flame they can never see. This black hole has been there since before our solar system formed, patiently waiting, growing, shaping the very structure of the Milky Way itself. And it's just one of an estimated 100 million black holes in our galaxy alone. Think about that number for a moment. 100 million black holes in our galaxy, each one representing the final fate of a star that lived for millions or billions of years before surrendering to the ultimate force of cosmic destruction. Each one a potential gateway to physics we don't yet understand. Each one harboring secrets that could unlock the deepest mysteries of space, time, and reality itself. And our galaxy? It's just one of trillions in the observable universe. The mathematics are staggering. Conservative estimates suggest there could be 40 quintillion black holes scattered throughout the cosmos. That's 40 followed by 18 zeros. To put this in perspective, if every black hole were a grain of sand, you could fill every beach on Earth and still have quintillions left over. But size and number aren't what make black holes the ultimate cosmic mystery. What makes them truly extraordinary is what they represent, the complete breakdown of everything we thought we understood about the universe. You see, black holes aren't just dense objects with strong gravity. They're regions where the very fabric of space-time becomes so warped that cause and effect, past and future, even the concepts of here and there begin to lose all meaning. They're places where Einstein's theory of relativity collides head-on with quantum mechanics, creating paradoxes that have kept the world's greatest minds awake at night for decades. Step too close to a black hole and time itself begins to slow down relative to the rest of the universe. Fall past the point of no return, the event horizon, and from the outside observer's perspective, you'll appear to slow down and redshift until you fade from view, frozen at the edge of oblivion for eternity. But from your own perspective, you'll experience something far stranger and more terrifying. Now, you might be wondering, why should any of this matter to us? Black holes are impossibly far away after all. The nearest known black hole to Earth is still over 1,600 light-years distant, so remote that its light left its vicinity during the time of the Roman Empire. But here's the profound truth. Black holes aren't just distant curiosities. They're fundamental to the very existence of the universe as we know it. Without them, galaxies wouldn't form, stars wouldn't cluster together. The cosmic web of matter that connects everything in the universe simply wouldn't exist. In a very real sense, black holes are the sculptors of cosmic architecture. They're the invisible artists that have shaped the universe into the magnificent tapestry of galaxies, stars, and planets that we see today. Without black holes, there would be no Milky Way. Without the Milky Way, there would be no solar system. And without our solar system, there would be no Earth, no us. Over the next several hours, we're going to embark on a journey that will take us from the heart of dying stars to the edge of known physics. We'll witness the birth of black holes in some of the most violent events the universe can produce. We'll explore how these cosmic vacuum cleaners consume matter and energy, sometimes producing jets of particles that stretch for thousands of light years across space. We'll dive into the quantum mechanical nightmare that black holes represent, where information might be destroyed, where virtual particles become real, and where the very concept of inside and outside breaks down completely. We'll examine recent discoveries that have revolutionized our understanding of these objects, from the first direct detection of gravitational waves produced by colliding black holes to the first actual photograph of a black hole's shadow captured by a telescope the size of Earth itself. But perhaps most importantly, we'll confront the deepest questions that black holes force us to ask. What is the true nature of space and time? Is information truly conserved in the universe, or can it be destroyed? Do black holes represent the ultimate end of matter, or are they gateways to somewhere else entirely? And here's the most mind-bending possibility of all. Some scientists now theorize that our entire universe might exist inside a black hole. That every black hole might contain a universe of its own. That the Big Bang itself might have been nothing more than the formation of a black hole in some higher dimensional space. If this sounds like science fiction, remember that just 50 years ago, black holes themselves were considered nothing more than mathematical curiosities. Today, we're tracking them, photographing them, and measuring the ripples they create in the fabric of space-time itself. What you're about to hear represents humanity's best current understanding of these cosmic enigmas, built from centuries of observation, experimentation, and theoretical work by some of the most brilliant minds who have ever lived. But it's also a story that's far from over. Every year brings new discoveries. Every observation reveals new mysteries. Every answer we find leads to 10 new questions that we never knew we should ask. The black holes are out there, waiting in the darkness between the stars. They've been there since the universe was young, and they'll be there long after the last star burns out and dies. They are simultaneously the universe's greatest destroyers and its most essential architects. They are the cosmic monsters that we're only beginning to understand. And now it's time to meet them face to face. Our story begins with death. Not the quiet, peaceful death of a small star like our sun, but the violent, spectacular death of a giant. Because to understand black holes, we must first understand the cosmic alchemy that creates them. A process so extreme, so violent, and so energetic that it can briefly outshine an entire galaxy of 400 billion stars. We must witness the birth of darkness itself. The birth of darkness. How black holes form. Deep in the constellation Cygnus, approximately 6,000 light-years from Earth, there exists a star that astronomers have designated as Eta Carinae. This is not an ordinary star. It's a monster, weighing in at roughly 150 times the mass of our Sun, burning through its nuclear fuel at a rate that our Sun couldn't match if it tried for 1 trillion years. Eta Carinae is what astronomers call a hypergiant, and it represents everything that makes stellar death both spectacular and terrifying. This star burns so brightly that if it were placed where our Sun is, it would vaporize Earth in an instant. Its surface temperature exceeds 40,000 degrees Celsius, nearly 7 times hotter than our Sun. And it's so unstable that it regularly erupts in explosions that can briefly make it one of the brightest objects visible in our night sky. But here's the truly remarkable thing about Eta Carinae: it's dying. And when it dies, it will create one of the most violent events the universe can produce. It will explode in what astronomers call a hypernova, an explosion so powerful that it will release more energy in 10 seconds than our Sun will produce in its entire 10 billion year lifetime. And from the ashes of that explosion, a black hole will be born. To understand how this happens, we need to take a journey deep into the heart of a dying star, where the fundamental forces of the universe wage their final battle. Because the formation of a black hole isn't just about a star running out of fuel, it's about the complete and total victory of gravity over every other force in nature. Let's start with the basics. Every star, from the smallest red dwarf to the largest hypergiant, exists in a state of perfect balance between two opposing forces. On one side you have gravity, the inward pull of the star's own massive weight trying to crush it down to a single point. On the other side, you have nuclear fusion, the outward pressure created by the conversion of hydrogen into helium in the star's core, which generates the energy that makes stars shine. For most of a star's life, this is a stable arrangement. The energy produced by fusion creates enough outward pressure to exactly counterbalance the inward pull of gravity. The star neither expands nor contracts. It simply exists in a state of equilibrium that can last for millions or billions of years. But this balance is temporary, and for massive stars like Eta Carinae, the end comes remarkably quickly. You see, the more massive a star is, the faster it burns through its nuclear fuel. Our Sun, with its relatively modest mass, has been burning hydrogen in its core for about 4.6 billion years and has enough fuel to continue for another 5 billion years. But a star like Eta Carinae, despite containing 150 times more fuel, will exhaust its hydrogen supply in just a few million years. When the hydrogen runs out, something remarkable happens. The star doesn't just die, it transforms. The core begins to contract under its own gravity, and the increased pressure and temperature from this contraction ignite a new type of nuclear fusion. Instead of converting hydrogen to helium, the star begins converting helium to carbon and oxygen. This new fusion process burns much hotter and faster than hydrogen fusion, causing the outer layers of the star to expand dramatically. The star becomes what astronomers call a red supergiant, a bloated monster that can grow large enough to swallow the orbit of Mars if it were placed in our solar system. But this reprieve is temporary. The helium burns out even faster than the hydrogen did, and once again the core contracts and heats up. Now the star begins burning carbon, creating even heavier elements like neon, magnesium, and silicon. Each new fuel burns faster and hotter than the last, and the star goes through these phases with increasing desperation. Silicon fusion, the final stage of stellar burning, creates iron. And iron is where the story takes a dramatic turn, because iron cannot be burned as nuclear fuel. When you try to fuse iron nuclei together, instead of releasing energy, the process actually requires energy. Iron fusion is an energy sink, not an energy source. So when a massive star's core fills up with iron, nuclear fusion simply stops. There is no more fuel, no more outward pressure. And gravity, which has been held at bay for millions of years, finally gets its chance to win. What happens next occurs with terrifying speed. Without the outward pressure of fusion to hold it up, the star's core begins to collapse under its own gravity. But this isn't a gradual process, it's a catastrophic collapse that happens in less than a second. In that single second, the core of a star the size of Earth collapses down to a sphere only about 12 miles in diameter. The matter becomes so compressed that a teaspoon of it would weigh as much as Mount Everest. Protons and electrons are crushed together so violently that they merge into neutrons, releasing a flood of neutrinos that carries away enormous amounts of energy. The density becomes so extreme that atomic structure itself breaks down. The empty space that normally exists between atomic nuclei disappears completely. What remains is a ball of pure neutron matter, a substance so dense that the laws of chemistry and atomic physics simply cease to apply. But for the most massive stars, even this incredible compression isn't enough to stop the collapse. If the stellar core exceeds what astronomers call the Tolman-Oppenheimer-Volkoff limit, roughly 3 times the mass of our Sun, then not even the neutron degeneracy pressure can halt gravity's relentless inward pull. At this point, something unprecedented happens. The collapse continues past the neutron star stage, past any known form of matter, past any mechanism that could possibly provide resistance to gravity's pull. The core shrinks smaller and smaller, past the size of a city, past the size of a mountain, past the size of a building. The matter becomes so dense that it warps the fabric of space-time itself. Imagine space-time as a stretched rubber sheet and mass as heavy balls placed on that sheet. Small masses create small dimples. Larger masses create deeper dimples. But the collapsing stellar core creates a dimple so deep that it forms a hole, a region where space-time curves back on itself, creating a one-way tunnel to nowhere. This is the birth of a black hole, a region of space where gravity has become so strong that nothing, not matter, not energy, not even light itself, can escape once it crosses a certain boundary. But the story doesn't end with the core collapse. Remember, we started with a star that was 150 times more massive than our Sun. Only the core, perhaps 3 to 10 solar masses, has collapsed into the black hole. The rest of the star, more than 100 solar masses of matter, is still there, and it's about to experience something unimaginable. When the core collapses and forms a black hole, it creates a shockwave that propagates outward through the star at thousands of kilometers per second. This shockwave carries with it energies that dwarf anything in our everyday experience. It's powered by the conversion of gravitational potential energy as matter falls into the newly formed black hole, and the amounts of energy involved are so vast that they challenge our ability to comprehend them. This shockwave rips through the star's outer layers, heating them to temperatures of billions of degrees and accelerating them to speeds approaching 10% of the speed of light. The star literally explodes from the inside out, hurling its outer layers into space in one of the most violent events the universe can produce, a supernova explosion. For a few brief weeks, this single exploding star can outshine an entire galaxy of 400 billion stars. The explosion can be seen from billions of light years away, appearing as a new star in the sky that gradually fades over months or years. Ancient Chinese astronomers recorded several such guest stars over the centuries, never knowing they were witnessing the birth of cosmic monsters from impossible distances. But the most remarkable thing about these explosions isn't their brightness, it's what they create. The tremendous heat and pressure of the supernova explosion forge elements that cannot be created any other way. Elements heavier than iron, gold, platinum, uranium are created in the first few seconds of the explosion and scattered into space by the blast. Every atom of gold in your jewelry, every atom of silver in your electronics, every atom of uranium in nuclear power plants was forged in the heart of an exploding star and scattered across the cosmos by a supernova explosion. We are, quite literally, made of star stuff. But more than that, we are made of the stuff of stellar death, the atomic remnants of cosmic catastrophes that occurred billions of years ago. And at the center of each explosion, hidden behind the brilliant light and expanding shockwaves, a black hole takes its first breath of existence. These stellar mass black holes typically weigh between 3 and 20 times as much as our Sun, but they're compressed into a region smaller than a major city. Their gravitational pull is so intense that they begin immediately affecting their surroundings, pulling in the material from the supernova explosion itself. As this material spirals into the black hole, it forms what astronomers call an accretion disk, a swirling vortex of superheated matter that glows brilliantly as it falls toward the point of no return. The friction between particles in this disk heats the material to millions of degrees, causing it to emit X-rays and gamma rays with such intensity that these newborn black holes become visible across vast distances of space. But stellar collapse isn't the only way black holes can form. In the early universe, when matter was distributed very differently than it is today, black holes could form through direct gravitational collapse without requiring a star at all. These primordial black holes could have masses ranging from microscopic to millions of times the mass of the Sun, and they might still be out there, invisible and undetected, scattered throughout the cosmos. Some theories suggest that intermediate mass black holes, weighing hundreds or thousands of solar masses, might form when stellar mass black holes merge together or when they consume nearby stars. Others propose that supermassive black holes, the giants that lurk at the centers of galaxies, might form when massive clouds of gas in the early universe collapse directly without ever forming stars. The truth is, we're still learning about all the different ways black holes can be born. Every new observation, every gravitational wave detection, every image captured by our most powerful telescopes reveals new mysteries about these objects and the processes that create them. What we do know is that black hole formation represents one of the most extreme phase transitions possible in physics. It's the moment when matter transitions from existing as particles, atoms, and molecules to existing as pure gravitational curvature of space-time. It's the instant when the familiar concepts of size, shape, and internal structure become meaningless, replaced by something that exists only as a distortion in the geometry of the universe itself. And once that transition occurs, once the event horizon forms and seals off the collapsed matter from the rest of the universe, we enter a realm where our normal understanding of physics begins to break down. Because beyond the event horizon lies a region that is, by definition, impossible to observe directly, a cosmic laboratory where the strangest predictions of general relativity and quantum mechanics play out in ways we're only beginning to understand. But to explore that strange realm, we need to first understand what an event horizon actually is. We need to comprehend what it means to have a boundary in space beyond which nothing can return. We need to grasp the concept of a point of no return written into the very fabric of reality itself. We need to understand why Albert Einstein called black holes the most perfect macroscopic objects there are in the universe, and why they terrified him so much that he spent years trying to prove they couldn't exist. The event horizon awaits our exploration. But before we cross that cosmic threshold, let's take a moment to appreciate the journey that brought us here. We've witnessed the death of giants, the forging of elements, and the birth of objects so strange that they challenge our most basic assumptions about the nature of reality. And we've only just begun to explore the true mysteries that black holes represent. Because if their formation is extraordinary, what lies beyond their event horizons is utterly beyond our everyday experience. It's a realm where time and space exchange roles, where the normal flow of causality breaks down, and where the very question of what happens to information when it falls into a black hole has sparked one of the most heated debates in modern physics. The stellar graveyard where black holes are born is just the beginning of our journey into the ultimate mystery of the cosmos. And as we prepare to cross the event horizon of understanding, one thing becomes clear: black holes aren't just the universe's way of disposing of matter it no longer needs. There's something far more profound and far more mysterious than that. The point of no return, understanding event horizons. In 1783, more than a century before Einstein would revolutionize our understanding of space and time, an English clergyman and natural philosopher named John Michell made a remarkable prediction. Using nothing more than Newton's laws of gravity and the recent discovery that light had a finite speed, Michell calculated that if you could compress enough mass into a small enough space, you would create an object with such strong gravity that not even light could escape from its surface. He called these hypothetical objects dark stars, and his calculations were remarkably prescient. What Michell had discovered, without knowing it, was the concept that would later become known as the event horizon, the boundary around a black hole beyond which escape becomes impossible. But Michell could never have imagined just how strange and counterintuitive these boundaries would turn out to be. Because event horizons aren't just invisible barriers in space, they're tears in the very fabric of reality, regions where the normal flow of time comes to a halt and where the fundamental nature of existence itself is called into question. Picture yourself approaching a black hole. Not one of the supermassive giants that lurk at the centers of galaxies, but a more modest, stellar mass black hole, perhaps 10 times the mass of our Sun. From a safe distance, it appears as nothing more than an absence, a spherical region of space where no light emerges, no stars shine, and no matter exists in any form you would recognize. This sphere of nothingness is the event horizon, and its size is determined by what physicists call the Schwarzschild radius. Named after Karl Schwarzschild, a German physicist who derived the mathematical description of black holes just months after Einstein published his theory of general relativity. Schwarzschild calculated these solutions while serving as a soldier on the Russian front during World War I and tragically died of an autoimmune disease just a few months later, never knowing that his work would become fundamental to our understanding of the universe. For our 10 solar mass black hole, the Schwarzschild radius works out to about 30 kilometers. This means the event horizon, the point of no return, forms a sphere roughly 60 kilometers in diameter. To put this in perspective, you could fit the entire city of Paris inside this black hole's event horizon with room to spare. But here's where things become truly bizarre. As you approach this invisible boundary, the laws of physics begin to behave in ways that challenge everything we think we know about space and time. Let's say you're falling toward the black hole feet first. Initially, everything seems normal. Space appears flat, time flows at its usual pace, and the distant stars shine with their familiar light. But as you get closer to the event horizon, you begin to notice something disturbing. The gravitational pull on your feet, which are slightly closer to the black hole than your head, becomes noticeably stronger than the pull on your head. This difference in gravitational force is called a tidal effect, and it begins to stretch your body like a piece of taffy. Physicists have given this process a rather whimsical name: spaghettification. At first, the stretching is subtle. You might feel like you're on a medieval rack, being pulled apart gradually. But as you get closer to the black hole, the tidal forces become more and more extreme. Your feet accelerate faster than your head, your body stretches thinner and thinner, and eventually, you're transformed into something resembling a strand of spaghetti, stretched across hundreds or thousands of kilometers of space. For a stellar mass black hole, like our 10 solar mass example, this spaghettification would begin to become uncomfortable long before you reach the event horizon. You would be torn apart by tidal forces while still thousands of kilometers away from the point of no return. But here's the truly mind-bending part. If you could somehow survive the tidal forces, or if you were falling into a supermassive black hole where the tidal effects are much gentler, you would experience something even more strange as you approach the event horizon. Time itself would begin to slow down. This isn't science fiction. It's a direct consequence of Einstein's general relativity. Gravity doesn't just bend space, it bends time as well. The stronger the gravitational field, the more slowly time passes relative to regions of weaker gravity. Near a black hole, where gravitational fields reach their maximum possible strength, time dilation becomes extreme. From your perspective, as you fall toward the black hole, your own time seems to flow normally. Your watch ticks at its usual pace, your thoughts proceed at their normal speed, and you don't feel like anything unusual is happening to time. But if you could look back at the outside universe, you would see something extraordinary. The distant stars would begin to speed up in their motions across the sky. If you had friends watching your descent from a safe distance, you would see them moving faster and faster, like a movie played at increasing speed. Their voices would become higher in pitch, their movements would appear frantic, and their entire timeline would begin to accelerate relative to your own. This effect becomes more and more pronounced as you approach the event horizon. Time in the outside universe appears to speed up more and more until eventually, from your perspective, you're watching the entire future history of the universe unfold in fast forward. But here's where the story takes an even stranger turn. Let's consider what your friends watching from a safe distance would see as you fall toward the black hole. From their perspective, the exact opposite happens. As you approach the event horizon, they would see you slowing down. Your movements would become more and more sluggish, your signals would take longer and longer to reach them, and the light from your body would become more and more redshifted, stretched to longer and longer wavelengths until it fades beyond the limits of their instruments to detect. In the final moments before you reach the event horizon, your friends would see you practically frozen in time, your image hovering just outside the point of no return, getting redder and dimmer until you simply fade from view. From their perspective, you never actually cross the event horizon at all. You're frozen there for eternity, a ghostly image gradually fading into infrared and then radio waves and finally into nothingness. This leads to one of the most profound paradoxes in black hole physics. From your perspective, you cross the event horizon in a finite amount of your own time, perhaps just a few minutes or hours depending on the mass of the black hole. But from the perspective of the outside universe, you never cross the event horizon at all. You're frozen there forever, gradually fading from view. So, which perspective is correct? Do you cross the event horizon or don't you? The answer, according to general relativity, is that both perspectives are equally valid. This is because there is no universal reference frame for time near a black hole. Time itself becomes relative in the most extreme way possible. Your experience of time and your friend's experience of time becomes so different that they're describing completely different realities. This paradox reveals something profound about the nature of event horizons. They're not physical barriers in the usual sense. There's no wall, no surface, no material boundary that you would encounter as you cross them. Instead, they're informational boundaries. They represent the limits of what the outside universe can ever know about what happens inside a black hole. Once information crosses an event horizon, it becomes causally disconnected from the rest of the universe. No signal, no message, no information of any kind can ever travel from inside the event horizon to the outside. In a very real sense, the interior of a black hole becomes a separate universe, cut off from everything else that exists. But event horizons come in different varieties depending on the type of black hole you're dealing with. The simple spherical event horizon we've been discussing applies to what physicists call a Schwarzschild black hole, a black hole that doesn't rotate and has no electric charge. But real black holes are more complicated than this. Most black holes in the universe are spinning, sometimes at tremendous rates. A spinning black hole, called a Kerr black hole, after the New Zealand mathematician Roy Kerr, who first described them mathematically, has a more complex structure than a simple Schwarzschild black hole. Around a spinning black hole, space-time itself is dragged around in the direction of rotation, creating a region called the ergosphere. Within the ergosphere, nothing can remain stationary relative to distant stars. Everything must move in the direction of the black hole's rotation, as if caught in a cosmic whirlpool. The boundary of the ergosphere is called the static limit, and it lies outside the event horizon. Between the static limit and the event horizon is a region where some truly bizarre physics occurs. It's theoretically possible for objects to enter this region, gain energy from the black hole's rotation, and escape with more energy than they had when they entered. This process, called the Penrose mechanism after physicist Roger Penrose, suggests that spinning black holes can actually serve as cosmic energy sources under the right circumstances. But perhaps the strangest prediction about spinning black holes concerns what happens at their very centers. While a non-rotating black hole has a point singularity at its center, a location where density becomes infinite and the laws of physics break down, a rotating black hole has what's called a ring singularity. This ring singularity creates the theoretical possibility of closed time-like curves, paths through space-time that loop back on themselves, potentially allowing travel to the past. Some physicists have speculated that if you could somehow survive the journey to the center of a rotating black hole, you might emerge not just in a different location, but in a different time, or even in a completely different universe. Of course, these are highly speculative ideas, and there are many reasons to think that such exotic effects might be prevented by unknown physics or quantum mechanical effects. But the mere fact that general relativity allows for such possibilities shows just how strange the environment near black holes can be. The event horizon also raises profound questions about the nature of information and the fundamental laws of physics. According to quantum mechanics, information cannot be destroyed. This principle, called unitarity, is one of the cornerstones of quantum theory. But black holes seem to present a direct challenge to this principle. When matter falls into a black hole, it carries information with it, information about its quantum state, its composition, its history. According to classical general relativity, this information is forever trapped behind the event horizon, cut off from the rest of the universe. And if the black hole eventually evaporates through Hawking radiation, as we'll explore in detail later, what happens to that information? This question, known as the black hole information paradox, has sparked one of the most intense debates in modern theoretical physics. Some physicists argue that information is indeed destroyed when it falls into a black hole, requiring us to modify our understanding of quantum mechanics. Others contend that information is somehow preserved, either escaping in the Hawking radiation or being encoded on the event horizon itself. Recent developments in string theory and holographic principles have suggested that the event horizon might not be the sharp boundary we once thought it was. Instead, some theories propose that information falling into a black hole is actually encoded on the horizon's surface, much like a hologram encodes three-dimensional information on a two-dimensional surface. This holographic principle suggests that everything that falls into a black hole might be perfectly preserved as information on the event horizon, visible to outside observers in an encoded form. From this perspective, black holes don't destroy information at all. They transform it into a form we don't yet know how to decode. But even more radical ideas have emerged from recent research. Some physicists now propose that event horizons might not exist at all in the classical sense. Instead, they suggest that quantum effects near what we think of as the event horizon create a firewall, a region of intense energy that would incinerate anything attempting to cross it. This firewall hypothesis is highly controversial and contradicts many of our established ideas about black holes. But it illustrates just how much we still don't understand about these objects and the boundaries they create in space-time. What we do know is that event horizons represent one of the most extreme environments in the universe. They're regions where the familiar concepts of space and time break down, where the normal flow of causality is severed, and where the fundamental laws of physics are pushed to their absolute limits. They're also remarkably simple in their mathematical description. Despite all the complexity of the matter that falls into them, despite all the violent processes that occur during their formation, black holes are characterized by just three properties: their mass, their electric charge, and their angular momentum. Everything else? The detailed composition of the matter that formed them, the history of their creation, the specific sequence of events that led to their birth, is completely erased. This remarkable simplicity is captured in what physicists call the no-hair theorem, which states that black holes have no distinguishing features beyond these three basic properties. In a sense, black holes are the ultimate democracy. It doesn't matter whether they formed from hydrogen, iron, exotic matter, or pure energy. Once matter crosses the event horizon, all that complexity is reduced to just three numbers. But this simplicity comes at a cost. The event horizon acts as a cosmic sensor, hiding the interior of the black hole from the rest of the universe. Whatever happens beyond that boundary, whatever exotic physics might occur near the singularity, whatever ultimate fate awaits the matter that falls in, remains forever hidden from outside observers. This cosmic censorship has profound implications for our understanding of the universe. It means there are regions of reality that are, by definition, unobservable. It suggests that the universe might contain vast realms of existence that are completely cut off from our own. And it raises the disturbing possibility that the laws of physics themselves might break down in ways we can never directly verify. As we prepare to explore what lies beyond the event horizon, we must grapple with the fact that we're entering a realm where observation becomes impossible, where theory must guide us through territories that can never be directly mapped, and where the very concepts of inside and outside begin to lose their meaning. The event horizon is more than just a boundary in space. It's a boundary in knowledge itself. It marks the limit of what the universe allows us to know about the cosmos we inhabit. And as we'll discover, the mysteries that lie beyond this boundary are stranger and more profound than anything we've encountered so far. But before we take that final plunge into the unknowable interior of a black hole, we need to explore how these cosmic monsters affect their surroundings. Because while we can never directly observe what happens inside a black hole, We can study the spectacular effects they have on the matter and energy around them. We can watch as they feed. We can measure the incredible energies they release as matter spirals to its doom. We can study the jets of particles they launch across thousands of light years of space. And we can explore how these invisible giants shape the very structure of the galaxies they inhabit. The event horizon may be a one-way boundary, but the region just outside it is one of the most violent, energetic, and spectacular environments in the entire universe. It's time to witness the feeding frenzy of cosmic monsters and to understand how these invisible predators announce their presence through some of the most luminous phenomena the cosmos has to offer. Giants in the dark, supermassive black holes. In the heart of the galaxy, Messier 87, located approximately 55 million light-years from Earth in the constellation Virgo, there lurks a monster so vast and so powerful that it defies comprehension. This is not the remnant of a single dead star, but something far more extraordinary. A supermassive black hole weighing as much as 6.5 billion of our suns, compressed into a region smaller than our solar system. In April 2009, this cosmic giant became the first black hole ever to be photographed directly. The image, captured by the Event Horizon Telescope, a network of radio telescopes spanning the entire globe, showed us something that many thought we would never see: the shadow of a black hole silhouetted against the glowing inferno of matter spiraling to its doom. But M87's central black hole is just one member of a population of cosmic giants that dwarf anything we've discussed so far. These supermassive black holes, weighing millions or billions of times more than our Sun, exist at the centers of virtually every large galaxy in the universe. They are the architects of cosmic structure, the invisible puppet masters that orchestrate the dance of hundreds of billions of stars, and the ultimate sources of some of the most energetic phenomena we observe in the cosmos. Yet their very existence poses a profound mystery. How did objects this massive form so early in the universe's history? How do they grow to such enormous sizes? And perhaps most remarkably, how do they manage to regulate the formation of stars across entire galaxies while remaining completely invisible? To understand supermassive black holes, we need to zoom out from the death of individual stars and consider the universe on a much grander scale. We need to explore how gravity operates not just on stellar masses, but on the scale of entire galaxies and galaxy clusters. And we need to confront the startling possibility that without these invisible giants, the universe as we know it, including our own existence, would be impossible. Let's begin with a journey to the center of our own galaxy, where a supermassive black hole called Sagittarius A star has been patiently waiting for us to discover it. 26,000 light-years from Earth, in the direction of the constellation Sagittarius, lies the exact center of the Milky Way galaxy. For most of human history, this region was invisible to us, hidden behind vast clouds of interstellar dust that block visible light. But in the past few decades, infrared and radio telescopes have given us the ability to peer through this cosmic fog and see what lies at the very heart of our galactic home. What we found there was extraordinary, a dense cluster of stars orbiting around what appeared to be nothing at all. These stars aren't moving in the gentle, circular orbits we see in most parts of the galaxy. Instead, they're whipping around in tight, elliptical paths at speeds that can exceed 5,000 kilometers per second, roughly 1.5% of the speed of light. Some of these stars complete their orbits in less than 20 years, despite being at distances from the galactic center comparable to the size of our entire solar system. For 3 decades, astronomers have been tracking the motions of these stars with ever-increasing precision. They've watched stars accelerate as they approach the galactic center, swing around something invisible, and then slow down as they retreat back into the outer regions of their orbits. It's like watching planets orbit the Sun, except that the Sun in this case is completely invisible and weighs 4 million times more than our actual Sun. The evidence for Sagittarius A star being a supermassive black hole became so overwhelming that in 2020 the Nobel Prize in Physics was awarded to Andrea Ghez and Reinhard Genzel for their decades-long campaign to map the orbits of stars around our galaxy's central black hole. Their work provided the most direct evidence possible for the existence of these cosmic giants. But Sagittarius A star is relatively modest as supermassive black holes go. At 4 million solar masses, it's actually on the smaller end of the supermassive scale. Some of the monsters that astronomers have discovered make our galaxy's central black hole look almost petite by comparison. Take, for example, the black hole at the center of the galaxy, IC 1101, located roughly 1 billion light-years from Earth. This cosmic leviathan weighs in at an estimated 40 billion solar masses, 10,000 times more massive than Sagittarius A star. If this black hole were placed at the center of our solar system, its event horizon would extend beyond the orbit of Neptune. Even more extreme is the black hole at the center of the quasar 21618, which astronomers estimate to weigh around 66 billion solar masses. This monster is so massive that its event horizon would encompass a region 11 times larger than Neptune's orbit. To put this in perspective, light would take more than a day to travel from one side of this black hole's event horizon to the other. But, perhaps most remarkably, these supermassive giants appear to have formed very early in the universe's history. Some of the most distant quasars we observe, powered by supermassive black holes feeding voraciously on surrounding matter, shine from when the universe was less than 1 billion years old. This presents a significant challenge to our understanding of how black holes grow. If supermassive black holes form from the collapse of individual stars, there simply hasn't been enough time in the universe's history for them to grow to such enormous sizes through accretion alone. A stellar mass black hole would need to feed continuously at the maximum possible rate for billions of years to reach the masses we observe in early quasars. But the universe wasn't even 1 billion years old when these giants already existed. This timing problem has led astronomers to propose several alternative formation mechanisms for supermassive black holes. One possibility is that they formed directly from the collapse of massive clouds of primordial gas in the early universe, bypassing the stellar phase entirely. These direct collapse black holes could have formed with initial masses of thousands or even hundreds of thousands of solar masses, giving them a significant head start on their growth. Another possibility involves the collapse of the first generation of stars in the universe. These primordial stars, formed from hydrogen and helium alone without any heavier elements, could have grown to masses hundreds of times larger than any star we see today. When such giants died, they might have left behind intermediate mass black holes that could serve as seeds for supermassive growth. Some theories even suggest that supermassive black holes might have formed from exotic processes in the very early universe, perhaps from the collapse of cosmic strings, or from phase transitions in the quantum vacuum, or from other high-energy phenomena that occurred during the first moments after the Big Bang. But regardless of how they formed, supermassive black holes have become the dominant gravitational influences at the centers of galaxies. They shape the distribution of stars, regulate the formation of new stars, and control the flow of gas and dust throughout their host galaxies. In many ways, galaxies are best understood not as collections of stars held together by dark matter, but as vast structures organized around their central supermassive black holes. This relationship between galaxies and their central black holes is one of the most surprising discoveries in modern astronomy. You might expect that black holes, being relatively tiny compared to their host galaxies, would have little influence on galactic evolution. After all, even the most massive supermassive black hole is still less than 1% of the mass of its host galaxy. But this intuition turns out to be completely wrong. Through a variety of feedback mechanisms, supermassive black holes can control star formation across their entire galaxies, determining not just where new stars form, but whether they form at all. The key to this influence lies in the tremendous energies released when matter falls into a supermassive black hole. As we discussed earlier, when matter spirals into a black hole, it forms an accretion disk that can heat up to millions of degrees and shine with the luminosity of trillions of stars. But this is just the beginning of the story. The intense magnetic fields generated in the accretion disk can accelerate particles to near the speed of light and launch them outward in narrow jets that extend for hundreds of thousands of light-years beyond the galaxy itself. These jets carry enormous amounts of energy, sometimes equivalent to the energy output of billions of stars, and they can dramatically alter the environment throughout the entire galaxy. When these jets slam into the surrounding interstellar medium, they create shock waves that heat the gas to such high temperatures that it becomes unable to cool down and collapse to form new stars. In effect, the supermassive black hole can shut off star formation across vast regions of its host galaxy. This process, called AGN feedback, where AGN stands for active galactic nucleus, appears to be crucial for explaining why massive galaxies stop forming stars. Without this feedback, computer simulations of galaxy formation produce galaxies that are far too massive and contain far too many stars compared to what we actually observe. The relationship between supermassive black holes and their host galaxies goes even deeper. Astronomers have discovered tight correlations between the mass of a galaxy's central black hole and various properties of the galaxy itself. The most famous of these is called the M-sigma relation, which links the mass of the central black hole to the velocity dispersion of stars in the galaxy's central bulge. This correlation is remarkably tight, with black hole masses varying in almost perfect lockstep with the properties of their host galaxies across a range of over 4 orders of magnitude in mass. This suggests that supermassive black holes and galaxies don't just coexist, they co-evolve, growing together in a complex dance of mutual influence that spans billions of years. But the influence of supermassive black holes extends far beyond their immediate host galaxies. Some of the most powerful objects in the universe are powered by matter falling into supermassive black holes, and these objects can affect the evolution of the cosmos on truly grand scales. Consider quasars, quasi-stellar radio sources that appear as brilliant points of light in our telescopes but can outshine entire galaxies. These objects are powered by supermassive black holes that are feeding voraciously on surrounding matter, converting a significant fraction of that matter's rest mass directly into energy through the accretion process. The most luminous quasars can shine with the brightness of more than 1 trillion suns, making them visible across billions of light-years of space. In fact, quasars are so bright that they serve as cosmic lighthouses, allowing us to study the state of the universe when it was just a fraction of its current age. But quasars aren't just bright, they're also incredibly violent. The jets they produce can extend for millions of light-years beyond their host galaxies, carving out enormous cavities in the intergalactic medium and affecting the formation and evolution of nearby galaxies. Some quasar jets are so powerful that they can influence galaxy formation across distances of tens of millions of light-years. These effects aren't just theoretical curiosities. Observations with X-ray telescopes have revealed that the space between galaxies in galaxy clusters is filled with hot gas that shows clear evidence of having been heated and stirred by the jets from central supermassive black holes. These jets create cavities and shock waves that can prevent gas from cooling and forming new stars, effectively regulating star formation on the scale of entire galaxy clusters. The energy scales involved in these processes are almost incomprehensible. A single active supermassive black hole can output more energy in 1 second than our Sun will produce in its entire 10 billion year lifetime. Over the lifetime of a galaxy, the total energy output from its central black hole can exceed the binding energy of the galaxy itself. This raises a profound question. If supermassive black holes are so energetic and influential, why don't they simply blow their host galaxies apart? The answer lies in the self-regulating nature of the feedback process. When a supermassive black hole becomes very active and starts producing powerful jets, those jets heat up the surrounding gas and reduce the rate at which new material can fall into the black hole. This causes the black hole's activity to decrease, which allows the gas to cool and start falling in again, which increases the black hole's activity, and so on. This feedback loop creates a natural thermostat that keeps galaxies in a delicate balance between growth and destruction. It's one of the most elegant examples of self-regulation in nature, operating on scales ranging from individual galaxies to the largest structures in the universe. But supermassive black holes don't just regulate star formation, they also play a crucial role in mixing and distributing heavy elements throughout the universe. The jets and outflows from active galactic nuclei can carry metals forged in stellar cores across vast distances, enriching the intergalactic medium with the elements necessary for planet formation and, ultimately, life. In this sense, supermassive black holes serve as cosmic recycling centers, taking in material from their surroundings, processing it through some of the most extreme physics in the universe, and then distributing the products across enormous volumes of space. They're simultaneously destroyers and creators, consumers and distributors, chaos and order. Perhaps nowhere is this dual nature more apparent than in the phenomenon of gravitational lensing around supermassive black holes. These objects are so massive that they bend light traveling near them, acting like enormous gravitational lenses that can magnify and distort the images of more distant objects. Sometimes this lensing effect creates multiple images of the same distant galaxy or quasar, allowing astronomers to study objects that would otherwise be too faint to observe. In other cases, it creates spectacular Einstein rings, perfect circles of light formed when a distant galaxy is almost perfectly aligned behind an intervening supermassive black hole. But gravitational lensing around supermassive black holes does more than just create pretty pictures. It provides us with one of the most direct ways to measure the masses of these objects and to study the distribution of matter in their immediate vicinity. By carefully analyzing how light is bent as it passes near a supermassive black hole, astronomers can map the gravitational field with extraordinary precision. This has led to some surprising discoveries. For example, studies of gravitational lensing have revealed that some supermassive black holes are surrounded by dense concentrations of dark matter in visible mass that interacts only through gravity. These dark matter concentrations, called cusps, may play important roles in feeding the black holes and regulating their growth. The study of supermassive black holes has also revealed unexpected connections between seemingly unrelated phenomena. For instance, astronomers have discovered that the formation of the first supermassive black holes in the early universe may have been closely linked to the reionization of cosmic hydrogen, the process by which the neutral hydrogen left over from the Big Bang was ionized by the first sources of light in the universe. The intense radiation from the first quasars, powered by rapidly growing supermassive black holes, may have contributed significantly to this reionization process. In effect, supermassive black holes may have helped to create the transparent universe we see today, clearing away the fog of neutral hydrogen that filled space during the cosmic dark ages. But perhaps the most profound implication of supermassive black hole research is what it tells us about the nature of cosmic evolution itself. The discovery that virtually every large galaxy contains a supermassive black hole at its center suggests that these objects are not mere accidents of cosmic evolution, but rather fundamental components of how the universe organizes itself on large scales. The tight correlations between black hole masses and galaxy properties, the crucial role of AGN feedback in regulating star formation, and the influence of supermassive black holes on cosmic reionization all point to the same conclusion. Supermassive black holes are not just passengers along for the ride in cosmic evolution, they're drivers of that evolution. This realization has fundamentally changed how astronomers think about galaxy formation and evolution. Modern cosmological simulations now routinely include detailed models of supermassive black hole growth and feedback, recognizing that without these components, the simulations fail to reproduce the observed properties of real galaxies. But even as our understanding of supermassive black holes has advanced dramatically, many fundamental questions remain unanswered. We still don't know exactly how the first supermassive black holes formed, or how they managed to grow so quickly in the early universe. We don't fully understand the detailed physics of AGN feedback or how supermassive black holes know when to turn on and off their regulatory processes. And we're only beginning to explore some of the most exotic possibilities that supermassive black holes represent. Could they serve as cosmic particle accelerators, producing some of the highest energy cosmic rays we observe? Might they be connected to mysterious phenomena like fast radio bursts or gamma-ray bursts? Could they harbor exotic physics that we haven't yet discovered? Recent observations have also revealed that supermassive black holes can do more than just regulate their host galaxies. They can also interact with each other in spectacular ways. When two galaxies merge, their central supermassive black holes eventually spiral toward each other, creating a binary system that can persist for millions of years before the final coalescence. The gravitational waves produced by merging supermassive black holes are among the most powerful signals in the universe, carrying energies that dwarf even the most energetic stellar processes. While these waves are too low in frequency to be detected by current ground-based detectors like LIGO, future space-based gravitational wave observatories will be able to observe these cosmic collisions from across the visible universe. When supermassive black holes do finally merge, the result is not just a single, more massive black hole, but also a tremendous release of energy that can kick the merged black hole out of its host galaxy entirely. These recoiling black holes can travel at speeds of thousands of kilometers per second, potentially wandering through intergalactic space as cosmic nomads. The study of supermassive black holes has also opened up new windows into fundamental physics. The extreme conditions near these objects provide natural laboratories for testing our understanding of gravity, space-time, and quantum mechanics in regimes that could never be reproduced on Earth. For example, the Event Horizon Telescope observations of M87's black hole have allowed astronomers to test Einstein's theory of general relativity in the strongest gravitational fields known to exist. So far, the observations are in excellent agreement with Einstein's predictions, but future observations may reveal departures from general relativity that could point toward new physics. Similarly, the study of matter falling into supermassive black holes provides insights into the behavior of matter under extreme conditions. The accretion disks around these objects reach temperatures of billions of degrees and densities that exceed those found in atomic nuclei. They're laboratories for plasma physics, magnetohydrodynamics, and high-energy astrophysics that push our understanding to its limits. But perhaps most importantly, supermassive black holes remind us of the profound interconnectedness of the universe. These objects, which exist as isolated points of infinite density according to general relativity, somehow manage to exert influence across billions of light-years of space. They connect the quantum mechanical world of subatomic particles to the cosmological world of galaxy clusters and large-scale structure. They're simultaneously the simplest objects in the universe, characterized by just 3 parameters, and the most complex, capable of influencing cosmic evolution in ways we're still discovering. They're the ultimate expression of gravity's power, yet they may also hold the key to understanding how gravity connects to the other fundamental forces of nature. As we prepare to delve deeper into the quantum mechanical mysteries that black holes represent, it's worth reflecting on how far our understanding has come. What began as mathematical curiosities in Einstein's equations have revealed themselves to be fundamental components of cosmic architecture, invisible sculptors that have shaped the universe we inhabit. But the mysteries they present are far from solved. In fact, the more we learn about supermassive black holes, the more we realize how much we still don't understand about these cosmic giants. And, as we'll discover in our next exploration, the quantum mechanical properties of black holes present puzzles that challenge our most basic assumptions about the nature of reality itself. The giants in the dark have revealed their presence through their gravitational influence and their spectacular feeding displays. But their deepest secrets lie in the realm where gravity meets quantum mechanics, where the familiar rules of physics break down, and where the very concept of information takes on new and mysterious meanings. To Matt, the Hawking revelation, black holes, and quantum physics. In 1974, a young physicist named Stephen Hawking made a discovery that would fundamentally change our understanding of black holes and shake the very foundations of modern physics. Working at the intersection of general relativity and quantum mechanics, Hawking uncovered a profound truth that no one had suspected: black holes are not truly black. They glow, they radiate energy, and most remarkably of all, they slowly evaporate away into nothingness. This discovery, now known as Hawking radiation, revealed that black holes are not the perfect cosmic vacuum cleaners that classical physics suggested. Instead, they are dynamic, quantum mechanical objects that exist in a constant state of creation and destruction, where the boundary between existence and non-existence becomes blurred in the most fundamental way possible. But Hawking's revelation did more than just show us that black holes can evaporate. It opened up a Pandora's box of paradoxes and puzzles that continue to challenge our understanding of reality today. These paradoxes strike at the heart of our most basic assumptions about information, causality, and the very nature of physical law. To understand how Hawking made his revolutionary discovery, we need to venture into one of the strangest realms of physics, the quantum vacuum. Despite its name, the quantum vacuum is not empty space. Instead, it's a seething foam of virtual particles that constantly pop into existence and annihilate each other in timescales so brief that they escape direct detection. This constant creation and destruction of virtual particles is not some theoretical curiosity, it's a fundamental feature of quantum mechanics that has been verified through countless experiments. The quantum vacuum generates measurable forces, affects the energy levels of atoms, and even causes uncharged metal plates to attract each other in a phenomenon called the Casimir effect. Under normal circumstances, these virtual particles appear in pairs. A particle and its antiparticle exist for a fleeting moment and then collide and annihilate each other, returning their borrowed energy to the vacuum. The process happens so quickly that it doesn't violate the conservation of energy thanks to Heisenberg's uncertainty principle, which allows energy to be borrowed from the vacuum for extremely short periods of time. But near the event horizon of a black hole, something extraordinary happens to this process. The intense gravitational field creates such extreme curvature in space-time that it can separate virtual particle pairs before they have a chance to annihilate each other. One particle from the pair falls into the black hole, while the other escapes to infinity. The escaping particle becomes real. It transforms from a virtual fluctuation into an actual particle that can be detected by distant observers. But where does the energy to make this particle real come from? It can't come from nothing, as that would violate the conservation of energy. Hawking's brilliant insight was to realize that the energy comes from the black hole itself. When one member of a virtual particle pair falls into the black hole, it carries negative energy with it, while the escaping particle carries positive energy. The black hole's mass decreases by exactly the amount of energy carried away by the escaping particle. In effect, the black hole is slowly paying for the creation of real particles by sacrificing some of its own mass. It's evaporating one quantum at a time through a process that operates at the very boundary between the classical world of general relativity and the quantum world of particle physics. This radiation that escapes from near the event horizon is what we now call Hawking radiation, and it has properties that are both elegant and deeply disturbing. The radiation has a perfect thermal spectrum. It's exactly what you would expect from a perfectly heated black body at a specific temperature. But this temperature is inversely related to the mass of the black hole. For a black hole with the mass of our Sun, the Hawking temperature works out to about 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills the universe. Such a black hole would absorb more energy from the cosmic background than it emits through Hawking radiation, causing it to grow rather than shrink. But for smaller black holes, the temperature becomes much higher. A black hole with the mass of a mountain would have a temperature of about 1 degree Kelvin. A black hole with the mass of a large asteroid would glow white hot, and a black hole with the mass of a small asteroid would shine brighter than the Sun before exploding in a burst of gamma rays. This inverse relationship between mass and temperature means that as a black hole evaporates and loses mass, it gets hotter and radiates faster, causing it to lose mass even more quickly. The process accelerates exponentially, culminating in a runaway evaporation that ends with the black hole completely disappearing in a final burst of energy. For a black hole with the mass of our Sun, this evaporation process would take an almost incomprehensibly long time. Roughly 1,067 years, a period so vast that it dwarfs the current age of the universe by a factor of more than a trillion. But the process is inexorable. Given enough time, even the most massive black holes will eventually evaporate away to nothing. This prediction has profound implications for the ultimate fate of the universe. In the far future, long after the last stars have burned out and died, long after protons themselves have decayed away, the universe will be dominated by black holes, slowly evaporating through Hawking radiation. And eventually, even these final remnants of the cosmos will disappear, leaving behind only a cold, empty space filled with the faint afterglow of their evaporation. But Hawking radiation presents us with more than just a prediction about the distant future. It creates a paradox that strikes at the very heart of quantum mechanics and our understanding of information. According to quantum mechanics, information is never destroyed. This principle, called unitarity, is one of the fundamental pillars of quantum theory. Every quantum process must be reversible in principle. Given perfect knowledge of the final state of a system, you should be able to work backward and determine what the initial state was. But Hawking radiation appears to violate this principle in the most dramatic way possible. When matter falls into a black hole, it carries information with it, information about its quantum state, its composition, its history. If the black hole then evaporates completely through Hawking radiation, and if that radiation has a perfectly thermal spectrum with no trace of the information that went into the black hole, then that information appears to be lost forever. This is the black hole information paradox, and it represents one of the deepest crises in modern theoretical physics. On one side, you have general relativity and Hawking's calculation, which suggests that information is indeed destroyed when black holes evaporate. On the other side, you have quantum mechanics, which insists that information must be conserved. Both theories have been tested extensively and have proven to be extraordinarily successful in their respective domains. But they seem to give contradictory answers when applied to the extreme environment near black holes. Something has to give, but what? Over the past 50 years, physicists have proposed numerous solutions to the information paradox, each more exotic than the last. Some suggest that information is somehow encoded in the Hawking radiation itself, hidden in subtle correlations that would require impossible precision to detect. Others propose that information escapes through microscopic wormholes that connect the black hole interior to distant regions of space. Perhaps the most radical proposal is that event horizons don't exist at all in the traditional sense. Instead, some theories suggest that the boundary around a black hole is actually a firewall, a region of such intense energy density that anything attempting to cross it would be instantly incinerated. This firewall hypothesis is deeply controversial because it contradicts one of the most cherished principles of general relativity, the equivalence principle, which states that someone falling freely in a gravitational field should not be able to detect that field locally. If firewalls exist, then someone falling into a black hole would definitely notice something dramatic happening at the event horizon. Another proposed solution involves the holographic principle, which suggests that all the information that falls into a black hole is actually encoded on its two-dimensional surface, much like a hologram encodes three-dimensional information on a flat surface. From this perspective, black holes don't destroy information, they transform it into a form we don't yet know how to decode. Recent developments in string theory have led to even more exotic proposals. Some physicists now suggest that black holes might be connected to distant regions of space through quantum entanglement, allowing information to escape through pathways that classical general relativity cannot describe. The ER-EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, suggests that Einstein-Rosen bridges, wormholes, and Einstein-Podolsky-Rosen correlations, quantum entanglement, are actually the same phenomenon viewed from different perspectives. If this is true, then entangled particles might be connected by microscopic wormholes, and black holes might be connected to distant locations through networks of quantum entanglement. But perhaps the most mind-bending possibility of all is that the information paradox is trying to tell us something fundamental about the nature of space and time themselves. Some physicists have proposed that space-time might be emergent, that it arises from more fundamental quantum information processes rather than being a basic feature of reality. From this perspective, black holes might represent regions where the usual emergent structure of space-time breaks down, revealing the underlying quantum information substrate that gives rise to our experience of space and time. The information paradox might not be a problem to be solved, but rather a window into a deeper level of reality. The quantum mechanical properties of black holes have also led to surprising insights about the nature of temperature and entropy. Hawking's calculation showed that black holes have a temperature, but it also revealed that they have an entropy, a measure of the amount of information or disorder they contain. Remarkably, the entropy of a black hole is proportional not to its volume, as you might expect, but to the area of its event horizon. This area law for black hole entropy was a completely unexpected result that has had profound implications for our understanding of information and thermodynamics. The fact that black hole entropy depends on area rather than volume suggests that the information content of any region of space might be fundamentally limited by the area of its boundary rather than by its volume. This insight has led to the development of the holographic principle, which proposes that any volume of space can be completely described by information encoded on its boundary. If the holographic principle is correct, then our three-dimensional experience of reality might be something like a holographic projection of information stored on a distant, two-dimensional surface. This would mean that the apparent three-dimensionality of space is an illusion, an emergent property of more fundamental two-dimensional physics. These ideas have found concrete expression in the AD-CFT correspondence, a mathematical relationship discovered by Juan Maldacena that connects certain theories of gravity in curved space-time to quantum field theories on the boundary of that space-time. This correspondence has provided a powerful tool for studying black holes and has led to many insights about the information paradox. Through AD-CFT, physicists have been able to study the evaporation of black holes in toy models where both sides of the correspondence can be calculated explicitly. These studies suggest that information is indeed preserved during black hole evaporation, but it's encoded in such a subtle way that it would be practically impossible. The quantum mechanics of black holes has also revealed unexpected connections to other areas of physics. For example, the study of Hawking radiation has led to insights about quantum field theory in curved space-time, the nature of vacuum states, and the relationship between thermodynamics and information theory. One of the most surprising discoveries is that the process of black hole evaporation appears to be related to quantum error correction, the same principles that are being developed for quantum computing. The idea is that the information that falls into a black hole is encoded in a highly redundant way across many degrees of freedom, allowing it to be recovered even if part of the system is lost. This connection between black holes and quantum information has led to a new field called quantum gravity phenomenology, which seeks to understand how quantum information principles might constrain theories of quantum gravity. Some researchers have even proposed that black holes might serve as natural quantum computers, processing information in ways that we're only beginning to understand. The study of Hawking radiation has also revealed that black holes have a kind of memory. When matter falls into a black hole, it leaves a subtle imprint on the black hole's exterior that can persist long after the matter itself has crossed the event horizon. These soft hair modes, as they're called, might provide a way for information to escape from black holes without violating any known physical principles. But perhaps the most profound implication of Hawking's discovery is what it tells us about the relationship between gravity and quantum mechanics. Hawking radiation emerges naturally from the combination of these two theories, suggesting that any complete theory of quantum gravity must take these effects into account. The fact that general relativity and quantum mechanics, when combined, predict that black holes evaporate suggests that the two theories are not independent but are intimately connected in ways we're still discovering. Black holes serve as laboratories where these connections become manifest, revealing physics that neither theory alone could predict. Recent experimental advances have brought us tantalizingly close to testing some aspects of Hawking's predictions. While we cannot directly observe Hawking radiation from astrophysical black holes, the effect is far too weak. Physicists have created analog black holes in laboratory settings using various condensed matter systems. These analog systems, which include flowing fluids, Bose-Einstein condensates, and even acoustic systems, exhibit event horizons and have been observed to produce radiation that closely mimics Hawking radiation. While these experiments don't prove that real black holes evaporate, they demonstrate that the physical principles underlying Hawking's calculation are sound. Future space-based gravitational wave detectors might be sensitive enough to detect the merger of primordial black holes formed in the early universe. If such black holes exist and have masses small enough to evaporate in the current epoch, their final moments of evaporation might produce detectable gravitational wave signals. The quantum mechanical properties of black holes have also opened up new possibilities for understanding the early universe. Some theories propose that the Big Bang itself might have been the time-reversed analogue of black hole evaporation, a process where quantum effects caused a region of extreme space-time curvature to expand and cool, creating the universe we observe today. This idea, sometimes called the Big Bounce, suggests that our universe might have emerged from the interior of a black hole in some higher dimensional space. If true, this would mean that black holes are not cosmic dead ends, but rather cosmic wombs, where new universes can be born. The study of black hole quantum mechanics has also led to insights about the nature of time itself. Near black holes, the usual notion of time as a universal parameter breaks down completely. Different observers experience time differently, and the very concept of simultaneous events becomes ambiguous. Hawking radiation emerges from quantum fluctuations near the event horizon, but these fluctuations exist in a complex superposition of states that span both the past and future light cones of the black hole. The radiation that we observe as coming from the black hole is actually the result of quantum interference between these different temporal pathways. This temporal complexity has led some physicists to propose that black holes might be windows into the nature of time itself. They might reveal that time, like space, is not fundamental but emergent, arising from more basic quantum information processes that don't respect our usual notions of temporal ordering. As we delve deeper into the quantum mechanical mysteries of black holes, we begin to see that these objects are far more than just gravitational anomalies. They are the universe's way of exploring the deepest questions about the nature of reality, information, and existence itself. They challenge our most basic assumptions about space, time, and causality. They force us to confront the possibility that the familiar world we experience might be just the surface manifestation of something far stranger and more wonderful. They suggest that the universe might be a vast quantum information processing system, with black holes serving as both the ultimate storage devices and the ultimate recycling centers. But before we can fully appreciate these cosmic implications, we need to understand how black holes interact with their environment in the here and now. We need to explore how these quantum mechanical oddities feed on matter and energy, and how they announce their presence through some of the most spectacular phenomena in the observable universe. The quantum realm has revealed that black holes are not the simple, classical objects that Einstein envisioned. They are dynamic, evolving, radiating entities that exist at the intersection of our two most successful theories of physics. And, as we'll discover, when these quantum mechanical giants begin to feed, they create some of the most violent and energetic displays that the cosmos has to offer. Feeding the based, accretion and jets. In the constellation of Cygnus, roughly 7,200 light-years from Earth, there exists a binary star system that has captivated astronomers for decades. At first glance, it appears unremarkable, just another point of light among the countless stars that populate our galaxy. But this system, known as Cygnus X1, harbors one of the most violent and spectacular phenomena in the universe, a black hole in the act of devouring its companion star. Cygnus X1 was the first object to be widely accepted as a black hole, and for good reason. Here, we can witness cosmic cannibalism in real time as a black hole, weighing roughly 20 times the mass of our Sun, systematically strips matter from a blue supergiant star in a process so violent and energetic that it outshines entire star-forming regions. But Cygnus X1 is just one example of a feeding black hole. Throughout the universe, these cosmic predators are engaged in a constant struggle to consume the matter around them, and the process of this consumption, called accretion, produces some of the most luminous and energetic phenomena we observe in the cosmos. To understand how black holes feed, we need to abandon our everyday intuitions about how objects fall toward massive bodies. When you drop a ball, it falls straight down. When the Earth orbits the Sun, it follows a predictable elliptical path. But when matter approaches a black hole, the story becomes far more complex and far more spectacular. The key insight is that most matter doesn't fall straight into a black hole. Instead, it approaches with some amount of angular momentum rotational motion that prevents it from falling directly inward. This angular momentum must be conserved, which means that as matter gets closer to the black hole and the gravitational field gets stronger, the matter must spin faster and faster to conserve its rotational energy. The result is that infalling matter naturally forms a swirling disk around the black hole, much like water circling a drain. But unlike water in your bathtub, the matter in these accretion disks is moving at a significant fraction of the speed of light and is heated to temperatures of millions or even billions of degrees. This heating occurs through friction between different layers of the disk moving at different speeds. The inner parts of the disk, closer to the black hole, orbit faster than the outer parts, creating shear forces that generate tremendous amounts of heat. The matter becomes so hot that it ionizes completely, forming a plasma that glows brilliantly across the electromagnetic spectrum. In the case of Cygnus X1, this process is particularly dramatic because the black hole is actively stripping material from its companion star. The blue supergiant, weighing about 20 times the mass of our Sun, is being gradually dismantled by the black hole's gravitational pull. Material from the star's outer layers streams toward the black hole in a process called Roche-Lobe overflow, named after the French astronomer Édouard Roche, who first described the physics involved. As this stellar material spirals into the black hole, it forms an accretion disk that reaches temperatures of over 100 million degrees Celsius. At these temperatures, the disk emits primarily in X-rays, making Cygnus X1 one of the brightest X-ray sources in our galaxy. The energy output is staggering. The accretion disk around this single black hole shines with the luminosity of roughly 400,000 suns. But the physics of accretion is far more complex than this simple picture suggests. The magnetic fields threading through the plasma in the accretion disk play crucial roles in determining how matter flows inward and how energy is extracted from the system. These magnetic fields are generated by the motion of the electrically conducting plasma itself, creating a complex magnetohydrodynamic environment where magnetic pressure, gas pressure, and gravitational forces all compete to determine the structure and evolution of the disk. The magnetic fields can become twisted and tangled by the differential rotation of the disk, storing enormous amounts of energy that can be released suddenly in explosive events. Sometimes, these magnetic field lines become so twisted that they snap and reconnect violently, accelerating particles to near the speed of light and launching them away from the disk in narrow, focused beams. These relativistic jets represent one of the most spectacular and energetic phenomena in the universe, capable of extending for millions of light-years beyond their host galaxies. The formation of these jets is intimately connected to the rotation of the black hole itself. When a black hole spins, it drags the surrounding space-time around with it in a phenomenon called frame dragging. This rotation can extract energy from the accretion disk and funnel it into collimated streams of particles that travel at speeds approaching 99.9% of the speed of light. The process by which this happens is called the Blanford-Zenyagek mechanism, named after the physicists Roger Blanford and Roman Zenyagek, who first described it mathematically. Magnetic field lines that thread through the accretion disk can become anchored to the rotating black hole, allowing the black hole's rotational energy to be extracted and converted into the kinetic energy of the jets. These jets are among the most efficient energy conversion mechanisms known in the universe. They can extract up to 42% of a black hole's rest mass energy and convert it into the kinetic energy of escaping particles. To put this in perspective, nuclear fusion, the process that powers stars, converts only about 0.7% of mass into energy. The most efficient chemical reactions convert even less. But accretion onto spinning black holes can achieve energy conversion efficiencies that are more than 50 times greater than nuclear fusion. The jets produced by feeding black holes come in many varieties depending on the mass of the black hole, the rate at which it's accreting matter, and the strength of the magnetic fields involved. Stellar mass black holes like Cygnus X1 typically produce relatively modest jets that extend for a few light-years beyond the black hole. But supermassive black holes can produce jets that span hundreds of thousands or even millions of light-years. One of the most spectacular examples is the jet emerging from the supermassive black hole at the center of the galaxy M87, the same black hole that was photographed by the Event Horizon telescope. This jet extends for over 5,000 light-years from the galaxy's center and contains enough energy to power the entire Milky Way galaxy for millions of years. The particles in these jets travel so close to the speed of light that relativistic effects become important. Time dilation means that processes within the jet appear to slow down when viewed from Earth. Length contraction means that the jet appears shorter than it actually is. And the relativistic Doppler effect means that light from parts of the jet moving toward us appears brighter and bluer, while light from parts moving away appears dimmer and redder. These relativistic effects can create optical illusions that make jets appear to be moving faster than the speed of light, a phenomenon called superluminal motion. This isn't actually faster than light travel, but rather an artifact of the geometry involved when objects move toward us at near light speeds. The energy carried by these jets is so enormous that they can significantly affect the evolution of their host galaxies and even entire galaxy clusters. When a jet slams into the surrounding interstellar or intergalactic medium, it creates shock waves that heat the gas to millions of degrees and can prevent it from cooling and forming new stars. This jet feedback is thought to be one of the primary mechanisms by which supermassive black holes regulate star formation in their host galaxies. Without this feedback, computer simulations suggest that galaxies would form far too many stars and would look very different from the galaxies we actually observe. But the feeding process isn't always steady and predictable. Black hole accretion can be highly variable, with dramatic changes in brightness occurring over timescales ranging from minutes to years. These variations tell us about the structure and dynamics of the accretion flow, and they provide some of the most direct probes we have of the environment immediately surrounding black holes. Sometimes, the accretion process becomes so unstable that it produces explosive outbursts. These can range from relatively modest flares that increase the black hole's brightness by a factor of a few to catastrophic events that can increase the luminosity by factors of thousands or even millions. One of the most dramatic examples of such an outburst occurred in the galaxy IC 3599, located about 900 million light-years from Earth. In 2010, astronomers observed this galaxy suddenly brighten by a factor of more than 1,000 in X-ray light. The outburst lasted for several years and was likely caused by a star wandering too close to the galaxy's central supermassive black hole and being torn apart by tidal forces. These tidal disruption events provide unique opportunities to study the feeding process of supermassive black holes. When a star approaches within about 100 times the black hole's event horizon radius, the tidal forces become strong enough to overcome the star's self-gravity and rip it apart. About half of the stellar debris falls into the black hole, while the other half is ejected at high speed. The material that falls into the black hole doesn't do so immediately. Instead, it forms a temporary accretion disk that can shine with the luminosity of billions of stars for months or years. As this disk evolves and the accretion rate decreases, astronomers can observe the entire life cycle of a feeding episode from beginning to end. These observations have revealed that the feeding process is far more complex than early theories suggested. The accretion flow can take many different forms depending on the rate at which matter is falling into the black hole, the temperature and density of the material, and the strength of the magnetic fields involved. At high accretion rates, the disk can become so hot and dense that radiation pressure becomes important, puffing up the disk and driving powerful winds that carry away a significant fraction of the infalling material. At low accretion rates, the disk can become very hot and tenuous, forming what's called a radiatively inefficient accretion flow, where most of the gravitational energy goes into heating the gas rather than producing radiation. The transition between these different accretion modes can produce dramatic changes in the black hole's appearance and energy output. A black hole that appears bright and active when it's accreting at high rates can become virtually invisible when the accretion rate drops, even though the black hole itself hasn't changed at all. This variability means that many black holes in the universe are currently sleeping, not because they're not there, but because they're not currently feeding. These dormant black holes can be awakened when new sources of material become available, either through the disruption of nearby stars, the merger of their host galaxy with another galaxy, or the simple gravitational capture of passing gas clouds. The study of black hole feeding has also revealed unexpected connections between the accretion process and the black hole's environment on much larger scales. The jets and outflows produced by feeding black holes can transport energy and matter across vast distances, affecting star formation in regions millions of light years away from the black hole itself. In galaxy clusters, the most massive, gravitationally bound structures in the universe, the supermassive black holes at the centers of the central galaxies produce jets that can carve out enormous cavities in the hot gas that fills the space between galaxies. These cavities, which can be larger than entire galaxies, represent some of the largest structures created by single objects in the universe. The energy required to create these cavities is staggering, typically equivalent to the energy output of billions of stars over millions of years. Yet this energy comes ultimately from matter falling into black holes that represent less than 1% of the mass of their host galaxies. It's a remarkable example of how small changes in one part of a system can have enormous consequences elsewhere. Recent observations have also revealed that the feeding process can be episodic, with periods of intense activity followed by long periods of quiescence. Some supermassive black holes show evidence of multiple cycles of activity, suggesting that the feeding process is regulated by feedback mechanisms that operate over timescales of millions or billions of years. These feedback cycles may be crucial for understanding how galaxies evolve over cosmic time. The energy injected by active black holes can heat the surrounding gas and prevent it from cooling and forming new stars. But eventually, the gas can cool and fall back toward the black hole, triggering a new episode of activity. This cycle of feeding, feedback, and renewal may be one of the key mechanisms that determines the properties of galaxies and their central black holes. It could explain why there are such tight correlations between black hole masses and the properties of their host galaxies, and it might be essential for understanding how the universe evolved from the smooth, nearly uniform conditions of the early cosmos to the complex, structured universe we see today. The feeding process has also provided us with some of our most direct tests of general relativity in strong gravitational fields. The material in accretion disks orbits so close to black holes that relativistic effects become clearly observable. Time dilation causes the orbital periods to differ from what Newtonian gravity would predict. Frame dragging causes the orbits to precess in ways that depend on the black hole's spin. And gravitational redshift causes the light from different parts of the disk to appear at different wavelengths. By carefully studying the X-ray emission from accretion disks, astronomers can measure these relativistic effects and test whether they match the predictions of Einstein's theory. So far, the observations are in excellent agreement with general relativity, providing some of the strongest confirmations of Einstein's theory in the most extreme gravitational environments known to exist. But perhaps most remarkably, the study of black hole feeding has revealed that these cosmic monsters are not just destroyers, but also creators. The energy they inject into their surroundings can trigger star formation in some regions while suppressing it in others. The heavy elements produced in the disks around black holes can be dispersed throughout galaxies, enriching the interstellar medium with the raw materials needed for planet formation. The jets and outflows from feeding black holes can also serve as cosmic particle accelerators, producing some of the highest energy particles observed in the universe. These cosmic rays can travel across intergalactic distances, carrying energy and information about the most extreme astrophysical processes to every corner of the cosmos. In this way, feeding black holes serve as both the ultimate consumers and the ultimate distributors of energy and matter in the universe. They consume everything that comes too close, but they also broadcast the energy from that consumption across vast distances, affecting the evolution of cosmic structure on scales ranging from individual stars to entire galaxy clusters. As we've seen, the process of black hole feeding is far more than just matter falling into a gravitational well. It's a complex interplay of gravity, magnetic fields, radiation pressure, and relativistic effects that produces some of the most energetic and spectacular phenomena in the universe. But our exploration of black hole feeding has revealed something even more profound. These objects are not isolated entities, but rather integral components of cosmic evolution. They shape the universe around them through their feeding activities, and they are shaped in return by the environment that feeds them. This intimate connection between black holes and their surroundings has become one of the central themes of modern astrophysics. And, as we'll discover in our next exploration, recent observations have not only confirmed many of our theoretical predictions about black holes, but have also revealed new mysteries that challenge our understanding of these cosmic enigmas. The feeding frenzy of black holes continues throughout the universe, a cosmic ballet of matter and energy that plays out across scales from event horizons to galaxy clusters. And thanks to revolutionary new technologies and observational techniques, we're now able to witness this dance in unprecedented detail, opening new windows into the most extreme physics the universe has to offer. Recent discoveries, from theory to reality. On September 14, 2015, at 5:15 a.m. Eastern Daylight Time, two identical detectors located 3,000 kilometers apart in Louisiana and Washington state recorded the same impossibly subtle signal. For just 0.2 of a second, these detectors, each consisting of laser beams traveling down 4-kilometer-long evacuated tubes, measured a distortion in space-time itself that was smaller than 1/10,000th the width of a proton. This minuscule distortion was the dying scream of two black holes that had collided and merged 1.3 billion years ago, sending ripples through the very fabric of space-time that had been traveling toward Earth since long before complex life existed on our planet. It was the first direct detection of gravitational waves, confirming a prediction that Einstein had made exactly 100 years earlier. But more than that, it was the moment when black holes transformed from theoretical constructs supported by indirect evidence into directly observable phenomena. For the first time in human history, we had heard the universe speak in gravitational waves, and the first words it spoke told us about the most extreme objects it contains. The detection, made by the Laser Interferometer Gravitational Wave Observatory, or LIGO, marked the beginning of a new era in astronomy. Just as the invention of the telescope 4 centuries earlier had opened our eyes to the cosmos, the development of gravitational wave detectors opened our ears to vibrations in space-time itself. But to appreciate the magnitude of this achievement, we need to understand just how difficult it is to detect gravitational waves. Einstein himself doubted whether they would ever be observed directly, writing in 1936 that there is no true radiation and that gravitational waves do not exist. He later corrected this mistake, but he maintained that the effects would be far too small to ever measure. Einstein wasn't wrong about the difficulty. Gravitational waves stretch and compress space itself, but the effect is extraordinarily weak. The LIGO detectors can measure changes in length that are 10,000 times smaller than the width of a proton. To put this in perspective, if the distance between Earth and the nearest star were measured to the accuracy of LIGO, the detector could detect a change the width of a human hair. Achieving this level of precision required some of the most sophisticated technology ever developed. Each LIGO detector uses laser interferometry to measure the distance between mirrors suspended at the ends of two perpendicular arms. When a gravitational wave passes through the detector, it stretches space in one direction while compressing it in the perpendicular direction, causing a measurable change in the interference pattern of the laser light. But the challenges go far beyond just building sensitive instruments. The detectors must be isolated from every possible source of vibration, from earthquakes thousands of kilometers away, to trucks driving on nearby highways, to waves crashing on distant shores. The mirrors must be suspended in vacuum chambers and kept stable to within fractions of atomic dimensions. The signal processing is equally challenging. The gravitational wave signals are buried in noise that can be millions of times stronger. Sophisticated computer algorithms, some based on machine learning techniques, are required to extract the signals from this noise and determine their astrophysical origins. When LIGO detected its first gravitational wave signal, designated GW1140914, the analysis revealed something remarkable. The signal was produced by two black holes weighing 36 and 29 times the mass of our Sun that had been orbiting each other in an ever-tightening spiral for millions of years. In the final moments before collision, these black holes were orbiting each other hundreds of times per second, their event horizons nearly touching, creating some of the most extreme conditions possible in the universe. The orbital velocities reached 60% of the speed of light, and the acceleration experienced by each black hole was more than 10,023 times the acceleration due to gravity on Earth. During the final tenth of a second before merger, the system radiated gravitational wave energy equivalent to the mass of 3 suns. This energy output briefly exceeded the total electromagnetic luminosity of all the stars in the observable universe. Yet this incredible energy was invisible to conventional telescopes. It could only be detected through its effects on space-time itself. The merger itself lasted only a few milliseconds, during which the two black holes spiraled together and formed a single, larger black hole weighing 62 solar masses. The missing 3 solar masses were converted entirely into gravitational wave energy, according to Einstein's famous equation mxc. The detection of GW5U914 was just the beginning. Since 2015, LIGO and its European counterpart Virgo have detected dozens of gravitational wave signals from merging black holes, each one providing new insights into these cosmic phenomena. These detections have revealed a universe far richer in black holes than anyone had expected. The masses of the merging black holes range from just a few times the mass of our Sun to nearly 100 solar masses. Some of these black holes have spins approaching the maximum allowed by general relativity, while others are spinning slowly or not at all. Perhaps most surprisingly, many of the detected black hole mergers involve black holes that are more massive than any stellar mass black holes known in our own galaxy. This suggests that either black holes can grow more massive than previously thought, or that the stellar evolution processes that create black holes operated differently in other galaxies or at earlier times in cosmic history. The gravitational wave detections have also provided the most precise tests of general relativity ever conducted in strong gravitational fields. The waveforms detected by LIGO match Einstein's predictions with extraordinary accuracy, confirming that general relativity correctly describes gravity even in the most extreme environments known to exist. But perhaps most remarkably, these detections have opened an entirely new window for studying black holes. Unlike electromagnetic radiation, which can be absorbed, scattered, or blocked by intervening matter, gravitational waves travel unimpeded from their sources to our detectors. They carry information about the most extreme moments of black hole collisions that could never be obtained through conventional astronomy. The success of gravitational wave astronomy has inspired a new generation of even more sensitive detectors. Future space-based observatories like the Laser Interferometer Space Antenna, LISA, will be able to detect gravitational waves from supermassive black hole mergers across the entire observable universe, opening new frontiers in our understanding of how these cosmic giants form and evolve. But even as gravitational wave astronomy was revolutionizing our understanding of black holes, another breakthrough was occurring that would provide the first direct visual evidence of these cosmic monsters. On April 10, 2009, astronomers around the world held their breath as the Event Horizon Telescope collaboration prepared to unveil the first photograph of a black hole. The image they revealed, a glowing ring of fire surrounding a dark shadow in the heart of the galaxy, M87, represented one of the greatest achievements in observational astronomy. The Event Horizon Telescope isn't a single instrument, but rather a network of radio telescopes spread across the globe, from Hawaii to Chile to Antarctica. By precisely synchronizing observations from these telescopes and combining their data through a technique called very long baseline interferometry, astronomers created a virtual telescope with the resolution of a single instrument the size of Earth. This Earth-sized telescope was necessary because black holes, despite their enormous masses, appear incredibly small when viewed from the vast distances of space. The black hole at the center of M87, despite being 6.5 billion times more massive than our Sun, subtends an angle in the sky equivalent to reading a newspaper on the Moon from Earth. The technical challenges involved in creating this image were staggering. The observations required atomic clock precision to synchronize telescopes on different continents. Massive amounts of data, equivalent to the entire internet traffic flowing through all of Europe, had to be recorded, shipped on hard drives, because no internet connection could handle the data rate, and carefully processed using supercomputers. The image processing itself required new algorithms and techniques. Unlike conventional photography, where light from an object directly creates an image, the Event Horizon Telescope observations measured the correlation between radio waves received at different telescopes. Converting these correlations into an image required sophisticated mathematical techniques and careful validation to ensure that the resulting picture was authentic. When the image was finally revealed, it showed exactly what Einstein's theory of general relativity had predicted: a dark shadow surrounded by a bright ring of glowing plasma. The shadow is the black hole's photon sphere, the region around the black hole where light can orbit in unstable circular paths. Any light that ventures closer than this boundary either falls into the black hole or is scattered away, creating the dark region we see. The bright ring surrounding the shadow is emission from the accretion disk, the swirling maelstrom of superheated matter spiraling into the black hole at nearly the speed of light. The asymmetry in the ring's brightness is caused by relativistic effects. Matter moving toward us appears brighter due to relativistic beaming, while matter moving away appears dimmer. The image provided the most direct test yet of Einstein's theory in the strong gravitational field regime. The size and shape of the shadow matched the predictions of general relativity to within the measurement uncertainties, providing further confirmation that our understanding of gravity is correct even in the most extreme environments. But the Event Horizon Telescope observations revealed more than just the shadow of the black hole. They also provided new insights into the structure of the accretion disk and the launching of relativistic jets. The observations showed that the magnetic fields near the black hole are strong enough to funnel matter and energy into the narrow jet that extends thousands of light years beyond the galaxy. Following the success of imaging M87's black hole, the Event Horizon Telescope turned its attention to an even more challenging target, Sagittarius A, the supermassive black hole at the center of our own galaxy. While SCEAR ACE is much closer to Earth than M87's black hole, it's also much smaller and more variable, making it a more difficult target for imaging. The observations of Stubby H required new techniques to deal with the rapid variability of the source. Unlike M87's black hole, which changes slowly over days or weeks, SCEAR can vary significantly over the course of a single observation. The imaging algorithms had to be modified to account for this variability and to extract a coherent picture from data taken over several hours. When the image of SCEAR AS was finally revealed in 2022, it showed a structure remarkably similar to M87's black hole, a dark shadow surrounded by a bright ring of emission. Despite being 1,500 times smaller and 1,000 times less massive than M87's black hole, SCEAR showed the same fundamental features predicted by general relativity. The similarity between these two very different black holes provided strong evidence that the physics of black holes is universal. Whether stellar mass or supermassive, whether actively feeding or relatively quiescent, black holes behave according to the same fundamental principles described by Einstein's theory. But the direct imaging of black holes is just one aspect of the observational revolution that has transformed our understanding of these objects. Advances in X-ray astronomy have provided new insights into the accretion processes around black holes, while improvements in optical and infrared telescopes have allowed astronomers to track individual stars as they orbit around supermassive black holes. The most dramatic example of this stellar orbital tracking comes from observations of the galactic center, where astronomers have now followed the orbits of dozens of stars around Sagittarius A for more than 2 decades. One star, designated S2 or SI2, has an orbit that brings it to within just 120 times the radius of the black hole's event horizon, closer than any star has ever been observed to approach a black hole. In 2018, S2 reached its closest approach to SCEAR, traveling at more than 7,500 kilometers per second, roughly 2.5% of the speed of light. At these speeds and in such a strong gravitational field, relativistic effects become clearly observable. The star's light was gravitationally redshifted by the black hole's gravity, exactly as predicted by general relativity. These observations provided another precise test of Einstein's theory, confirming that general relativity correctly describes the motion of matter in strong gravitational fields. They also allowed astronomers to measure the mass of Sestrar with unprecedented precision, determining that it weighs 415 million times the mass of our Sun. But, perhaps most remarkably, these stellar orbital observations have allowed astronomers to test some of the more exotic predictions of general relativity. The orbit of S2 shows clear evidence of relativistic precession, the slow rotation of the orbit's orientation caused by the curvature of spacetime around the black hole. Future observations may be sensitive enough to detect even more subtle effects, such as the lens, Thirring precession caused by the rotation of the black hole itself. These measurements could provide the first direct determination of a supermassive black hole spin, opening new avenues for understanding how these objects form and evolve. The past decade has also seen remarkable advances in our understanding of black hole formation through observations of stellar explosions. New types of supernovae and hypernovae have been discovered that may represent different pathways to black hole formation, while observations of gamma-ray bursts have provided insights into the most energetic black hole formation events. Perhaps most intriguingly, astronomers have begun to discover intermediate mass black holes, objects with masses between stellar mass and supermassive black holes that had long been predicted but rarely observed. These discoveries are providing new insights into how supermassive black holes might have formed in the early universe. Advanced computer simulations have also revolutionized our theoretical understanding of black holes. Modern simulations can model the merger of two black holes with unprecedented accuracy, predicting not only the gravitational wave signals they produce, but also the electromagnetic emission from any surrounding matter. These simulations have revealed that black hole mergers can be far more complex than previously thought. The merged black hole can receive a kick from the asymmetric emission of gravitational waves, potentially ejecting it from its host galaxy entirely. Some simulations suggest that thousands of these rogue black holes might be wandering through intergalactic space. The combination of gravitational wave detections and electromagnetic observations has created the new field of multi-messenger astronomy. When neutron stars merge, they produce both gravitational waves and electromagnetic emission, allowing astronomers to study these events with multiple types of detectors simultaneously. While most neutron star mergers produce neutron stars or low-mass black holes, some may produce more massive black holes, providing new insights into black hole formation mechanisms. Future gravitational wave detectors may be sensitive enough to detect the formation of stellar mass black holes directly, observing the moment when a massive star's core collapses beyond the neutron star threshold. Recent observations have also revealed unexpected connections between black holes and other astronomical phenomena. Some fast radio bursts, brief, intense pulses of radio emission, may be produced by matter falling into black holes. Some gamma-ray bursts may be powered by the formation of new black holes or by the sudden activation of dormant ones. The study of black hole jets has also advanced dramatically thanks to new radio interferometry techniques. Astronomers can now trace these jets from their origins near the black hole's event horizon to their termination points thousands of light years away, providing unprecedented insights into how these cosmic particle accelerators operate. Perhaps most remarkably, advances in computational power have allowed astronomers to simulate entire galaxies and their central black holes over billions of years of cosmic evolution. These simulations have revealed the complex feedback loops between black hole growth and galaxy formation, showing how these seemingly disparate phenomena are intimately connected. The next decade promises even more revolutionary discoveries. Next-generation gravitational wave detectors will be sensitive enough to detect black hole mergers from across the observable universe. Space-based telescopes will be able to study black holes in wavelengths of light that are blocked by Earth's atmosphere. And new theoretical insights continue to push the boundaries of our understanding. One of the most exciting prospects is the possibility of observing matter as it crosses a black hole's event horizon. While we can never directly see what happens inside a black hole, future observations may be sensitive enough to track matter during its final moments before it disappears forever behind the event horizon. These observations could provide crucial tests of our understanding of black hole physics and might even reveal new physics beyond general relativity. They could help resolve long-standing puzzles like the information paradox and provide insights into the quantum mechanical nature of gravity. The transformation of black holes from theoretical curiosities to directly observable phenomena represents one of the greatest triumphs in the history of science. In just a few short years, we've gone from inferring the existence of black holes through their gravitational effects to actually seeing their shadows and hearing their collisions. But as remarkable as these discoveries have been, they've also revealed how much we still don't know about these cosmic enigmas. Each new observation raises new questions, each new detection reveals new mysteries, and each new insight opens new avenues for exploration. The recent discoveries have confirmed that black holes are real, that they behave as Einstein predicted, and that they play fundamental roles in cosmic evolution. But they've also shown us that the universe is far stranger and more wonderful than we ever imagined, filled with phenomena that push the boundaries of physics and challenge our understanding of reality itself. As we stand on the threshold of even more revolutionary discoveries, one thing is clear: the age of black hole astronomy has only just begun. The cosmic monsters that once existed only in the equations of theoretical physicists are now the subjects of direct observation, detailed study, and continuing mystery. And, as we'll discover, these observations are not just telling us about black holes, they're revealing fundamental truths about the nature of information, the structure of space-time, and the ultimate fate of everything in the universe. The information paradox. What happens to matter? Imagine you have a book, any book, perhaps it's a novel, a textbook, or even a cookbook. Now imagine that you throw this book into a fire and watch it burn. The paper chars, the ink vaporizes, and eventually nothing remains but a small pile of ash and some gases dispersed into the atmosphere. Has the information in that book been destroyed? According to the fundamental principles of physics, the answer is no. Every letter on every page, every detail of the book's structure, even the precise arrangement of atoms that made up the ink, all of this information still exists, encoded in the quantum states of the ash, the dispersed gases, and the light that radiated away from the fire. In principle, if you had perfect knowledge of the quantum state of every particle produced by the burning, and if you had unlimited computational resources, you could work backward and reconstruct not just the book, but every detail of how it burned. The information would be scrambled and distributed, but it would not be lost. This principle, that information can never be truly destroyed, is one of the cornerstones of quantum mechanics. It's called unitarity, and it underpins our entire understanding of how the quantum world works. Every physical process must be reversible in principle. Information can be scrambled, encrypted, or spread across vast distances, but it cannot simply vanish from existence. But black holes present a profound challenge to this principle. When that book falls into a black hole, where does its information go? What happens to every quantum bit of data that crosses the event horizon? And if the black hole eventually evaporates away through Hawking radiation, as we've learned it must, what happens to all the information it ever consumed? This is the black hole information paradox, and it represents perhaps the deepest crisis in modern theoretical physics. It's a puzzle that has consumed the world's greatest minds for more than half a century, spawning new theories, challenging our most basic assumptions about reality, and forcing us to confront the possibility that either quantum mechanics or general relativity or both might be fundamentally incomplete. The paradox arises from the combination of two seemingly unassailable facts. First, according to general relativity, anything that falls into a black hole crosses the event horizon and disappears from the outside universe forever. The information it carried becomes causally disconnected from everything else that exists, sealed away behind a boundary that nothing can cross from the inside out. Second, according to Hawking's calculation, black holes emit thermal radiation that causes them to slowly evaporate. This radiation has a perfectly thermal spectrum. It's completely random, carrying no information about what fell into the black hole. If information cannot escape through this radiation, and if the black hole eventually disappears completely, then the information that fell in appears to be lost forever. But this can't be right, according to quantum mechanics. Information cannot be destroyed, so something has to give. Either general relativity is wrong about event horizons, or quantum mechanics is wrong about information conservation, or our understanding of Hawking radiation is incomplete. To understand why this paradox is so profound, let's follow the journey of information as it approaches a black hole. Consider Alice, an intrepid explorer who decides to jump into a black hole while carrying that book we imagined earlier. From Alice's perspective, nothing particularly dramatic happens as she crosses the event horizon. She doesn't encounter any barrier, doesn't experience any sudden change in physics, and doesn't notice the moment when she passes the point of no return. From Alice's point of view, the book she's carrying continues to exist in a perfectly normal way. She can still read it, still turn its pages, still access all the information it contains. The laws of physics appear to work normally, and there's no obvious reason why the book's information should be any different than it was before crossing the event horizon. But from the perspective of Bob, who remains safely outside the black hole, the situation looks very different. Bob never sees Alice cross the event horizon at all. Instead, he sees her image freeze at the boundary, gradually redshifting to longer and longer wavelengths until she simply fades from view. From Bob's perspective, Alice never enters the black hole. She's permanently frozen at the event horizon. So where is the book's information? From Alice's perspective, it's safely inside the black hole, continuing to exist in a perfectly normal way. From Bob's perspective, it's encoded in the increasingly redshifted light near the event horizon, gradually spreading out and becoming undetectable but never actually disappearing. This strange situation becomes even more puzzling when we consider Hawking radiation. If the black hole eventually evaporates completely, what happens to the information? From Alice's perspective, the information went into the black hole and should somehow be encoded in the Hawking radiation that comes out. But Hawking's original calculations suggested that this radiation is completely thermal. It carries no information about what went into the black hole. This leads to an apparent contradiction. The information must be conserved according to quantum mechanics, but there seems to be no way for it to escape from the black hole according to general relativity. Over the past 50 years, physicists have proposed numerous solutions to this paradox, each more exotic and mind-bending than the last. Let's explore some of the most prominent proposals and see how they attempt to resolve this fundamental crisis in our understanding of physics. One of the earliest proposals was that information is indeed encoded in the Hawking radiation, but in such a subtle way that it would be impossible to detect with any realistic measurement. According to this idea, the radiation only appears thermal when averaged over long periods of time. On shorter timescales, it might contain tiny correlations that encode information about what fell into the black hole. The problem with this proposal is quantitative. Calculations suggest that these correlations would be exponentially small, so tiny that detecting them would require measuring the radiation with impossible precision. It would be like trying to reconstruct a book by analyzing the noise in a radio signal that's been scrambled by a process more complex than the entire observable universe. A more radical proposal is that the event horizon itself doesn't exist in the way that classical general relativity suggests. Instead, the boundary around a black hole might be a firewall, a region of such intense energy density that anything attempting to cross it would be instantly incinerated. This firewall hypothesis solves the information paradox by preventing information from ever actually entering the black hole. Instead, information is destroyed at the event horizon and then re-emitted in the Hawking radiation. But this solution comes at a tremendous cost. It requires abandoning the equivalence principle, one of the fundamental pillars of general relativity. The equivalence principle states that there's no way to distinguish between gravitational acceleration and any other kind of acceleration. Someone falling freely toward a black hole shouldn't be able to detect any local effects of the gravitational field. But if a firewall exists at the event horizon, then falling into a black hole would be a very noticeable experience indeed. Another proposal involves the holographic principle, which suggests that all the information in any volume of space can be encoded on the boundary of that volume. Applied to black holes, this means that information that appears to fall into the black hole might actually be encoded on the event horizon's surface. From this perspective, the black hole's interior doesn't contain information in the usual sense. Instead, the information is stored as a hologram on the two-dimensional surface of the event horizon. The three-dimensional interior that Alice experiences might be an emergent phenomenon, a kind of holographic projection created by the information encoded on the boundary. This holographic solution is mathematically elegant and has found support through the AD-CFT correspondence, a precise mathematical relationship between certain theories of gravity and quantum field theories. In the context of AD-CFT, the evaporation of a black hole can be shown to be a unitary process that preserves information, even though the mechanism by which this happens is incredibly complex. But even more radical proposals have emerged from recent research. Some physicists now suggest that the interior of a black hole might be connected to distant regions of space through quantum entanglement. When Alice falls into the black hole, she might not disappear into an isolated interior, but rather emerge in some distant region of the universe connected to the black hole through quantum wormholes. This idea, encapsulated in the ER-EPR conjecture proposed by Juan Maldacena and Leonard Susskind, suggests that Einstein-Rosen bridges, wormholes, and Einstein-Podolsky-Rosen correlations, quantum entanglement, are actually the same phenomenon viewed from different perspectives. If this is correct, then black holes might not be cosmic dead ends, but rather cosmic transit systems that connect different regions of space-time. Another possibility is that the information paradox is trying to tell us something fundamental about the nature of space and time themselves. Some physicists have proposed that space-time might not be fundamental, but rather emergent, arising from more basic quantum information processes. From this perspective, the smooth, curved space-time of general relativity might be an approximation that breaks down near black holes where the underlying quantum information structure becomes visible. The information paradox might not be a problem to be solved, but rather a window into a deeper level of reality where space and time emerge from quantum information. Recent developments in quantum error correction have provided new insights into how information might be preserved in black holes. The idea is that information falling into a black hole is encoded redundantly across many different degrees of freedom, allowing it to be recovered even if part of the system is lost or corrupted. This quantum error correction approach suggests that black holes might function like natural quantum computers, processing information in ways that preserve it even through the most extreme physical processes. The Hawking radiation would then carry information about the black hole's interior, but in a form so scrambled and encoded that extracting it would require quantum computational resources that scale exponentially with the black hole's size. But perhaps the most mind-bending possibility is that the information paradox reveals something profound about the nature of observation and measurement in quantum mechanics. Some interpretations suggest that information is only real when it's observed or measured. From this perspective, information that falls into a black hole becomes unobservable and therefore, in some sense, ceases to exist. This interpretation challenges our usual notion that information has an objective existence independent of observers. Instead, it suggests that information might be fundamentally relational, existing only in the context of systems that can observe or interact with it. The debate over the information paradox has also led to unexpected insights about the relationship between gravity and thermodynamics. Black holes have temperature and entropy, suggesting deep connections between gravitational physics and statistical mechanics. Some physicists have proposed that gravity itself might be an emergent phenomenon arising from the thermodynamic properties of quantum information. If gravity is emergent, then the information paradox might be resolved by recognizing that our usual notions of inside and outside a black hole are approximations that break down when quantum effects become important. The information might never actually fall into the black hole in the first place, but rather remain encoded in the quantum correlations that give rise to the apparent gravitational field. Recent experimental analogies have provided new ways to study the information paradox. physicists have created analog black holes using various condensed matter systems from flowing fluids to Bose, Einstein condensates. While these systems don't contain actual event horizons, they exhibit similar physics and can help test theoretical predictions about information flow in black hole analogies. These analog systems have demonstrated that information can indeed be preserved in black hole-like systems, but through mechanisms that are far more complex than early theories suggested. The information emerges in subtle correlations between different parts of the system, requiring sophisticated quantum mechanical analysis to detect. The information paradox has also influenced our understanding of quantum entanglement and its role in space-time geometry. Recent research suggests that entanglement between different regions of space might be what gives rise to the connected geometry of space-time itself. From this perspective, the smooth space-time of general relativity emerges from quantum entanglement, and black holes represent regions where this entanglement becomes maximally scrambled. One of the most active areas of research involves studying the entanglement structure of Hawking radiation. If information is preserved during black hole evaporation, then the early and late Hawking radiation must be entangled in a very specific way. Understanding this entanglement structure might provide the key to resolving the information paradox, but the paradox has implications that extend far beyond black holes. If information can be destroyed in black holes, then it might be destroyed in other physical processes as well. This would require a fundamental revision of quantum mechanics and could have implications for everything from quantum computing to our understanding of the arrow of time. Conversely, if information is preserved in black holes through some exotic mechanism, then similar mechanisms might operate in other areas of physics. This could lead to new insights about quantum gravity, the nature of space-time, and the fundamental structure of physical law. The information paradox also raises profound questions about the nature of physical reality itself. If information that falls into a black hole continues to exist but becomes permanently unobservable, what does it mean for something to exist if it can never be detected or influence anything else? This question touches on some of the deepest issues in the philosophy of physics. Does the universe contain objective facts independent of what can be observed? Or is physical reality fundamentally limited to what can be measured and detected? Different solutions to the information paradox imply different answers to these questions. Some solutions preserve an objective reality where information always exists, regardless of whether it can be observed. Others suggest that reality is fundamentally observer-dependent and that unobservable information doesn't truly exist. The stakes involved in resolving the information paradox couldn't be higher. At issue is not just our understanding of black holes, but our most basic concepts of space, time, information, and reality itself. The resolution of this paradox is likely to require new physics that goes beyond both general relativity and quantum mechanics as we currently understand them. Recent advances in quantum gravity research, particularly in string theory and loop quantum gravity, are beginning to provide new tools for attacking the information paradox. These approaches suggest that the smooth spacetime of classical general relativity might be an approximation that breaks down at the Planck scale where quantum gravitational effects become important. If spacetime itself has a quantum structure at the smallest scales, then the formation and evaporation of black holes might involve processes that are not captured by classical general relativity. The information paradox might be resolved by understanding how quantum spacetime behaves in the extreme environment near black holes. But regardless of how the information paradox is ultimately resolved, its investigation has already revolutionized our understanding of physics. It has forced physicists to think more carefully about the relationship between gravity and quantum mechanics, leading to new insights about holography, entanglement, and the emergence of space-time. The paradox has also highlighted the importance of thought experiments in theoretical physics. By considering what happens when quantum mechanics meets general relativity in the extreme environment of black holes, physicists have uncovered deep questions about the nature of physical law that might never have been discovered through experiment alone. As we stand on the threshold of new observational capabilities, from space-based gravitational wave detectors to quantum computers that might be able to simulate black hole physics, the information paradox continues to drive theoretical research and experimental investigation. The question of what happens to information when it encounters a black hole remains one of the deepest unsolved problems in physics. But the search for an answer has already transformed our understanding of the universe and continues to reveal new mysteries about the nature of reality itself. Whether information is preserved, destroyed, or transformed in ways we can't yet imagine, the black hole information paradox has shown us that these cosmic monsters are more than just gravitational anomalies. They are laboratories where the deepest questions about existence itself are played out on a cosmic stage, forcing us to confront the limits of our knowledge and the mysteries that lie at the heart of physical law. And as we'll discover in our final exploration, these questions about information and black holes are intimately connected to the ultimate fate of everything in the universe, including the cosmos itself. As we reach the end of our journey into the heart of cosmic darkness, it's time to confront perhaps the most profound question of all. What role will black holes play in the ultimate fate of the universe? When the last star has burned out, when the final planet has been stripped from its orbit, when even the protons that make up matter itself have decayed away, what will remain? The answer, according to our best current understanding of physics, is both elegant and terrifying. In the end, black holes will inherit the universe. To understand this cosmic inheritance, we need to take a journey not just through space, but through time, vast expanses of time that dwarf the entire history of the universe so far. We need to explore scenarios that play out over periods so long that the entire age of the universe, from the Big Bang to today, represents less than the blink of an eye. This is the story of the universe's far future, a tale that stretches across more than 100 orders of magnitude in time, from the mere billions of years we've already experienced to the incomprehensible eons that lie ahead. And at the center of this story are the black holes, patiently waiting in the darkness, destined to be the final witnesses to the cosmic drama that began with the Big Bang. Let's begin our journey into deep time by considering what we can observe about the universe's current state and trajectory. The cosmos is approximately 1328 billion years old, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. It's expanding, and that expansion is accelerating, driven by the mysterious dark energy that comprises roughly 68% of all matter and energy in existence. For now, the universe is a vibrant, active place. Stars are forming, galaxies are merging, planets are being born, and at least in one small corner we know about, life has emerged and developed consciousness capable of contemplating its own cosmic origins. But this golden age of cosmic activity will not last forever. The first major transition in the universe's future will occur in what cosmologists call the stelliferous era, the age of star formation. We're currently living in this era, but it's already beginning to wind down. Star formation peaked roughly 3 billion years ago and has been declining ever since as the universe's supply of hydrogen gas gets locked up in existing stars or dispersed too thinly to collapse into new ones. In about 100 billion years, roughly 7 times the current age of the universe, the last stars will form. After that, the universe will be left with only the stellar remnants, white dwarfs, neutron stars, and black holes. No new sources of energy will be created through nuclear fusion, and the cosmos will begin its long slide toward thermodynamic equilibrium. But even after star formation ceases, stellar remnants will continue to shine for an enormous period of time. Red dwarf stars, the smallest and longest-lived main sequence stars, can continue burning for trillions of years. White dwarf stars, the cooling remnants of sun-like stars, will take even longer to fade away, perhaps 10 months at 15 years to cool to the temperature of the cosmic microwave background. During this extended twilight of the stars, the universe will be a dimmer but still dynamic place. Galaxies will continue to merge and evolve. Brown dwarfs and planets will occasionally collide with white dwarfs, causing them to flare briefly back to life. And the supermassive black holes at the centers of galaxies will continue to grow, albeit slowly, by capturing stray matter and merging with other black holes. But even this extended stellar afterglow will eventually fade. In roughly 10-15 years, 1,000,000 billion times longer than the universe has existed so far, even the longest-lived red dwarf stars will exhaust their fuel and die. The last white dwarfs will cool to invisibility, becoming cold, dark spheres of crystallized carbon and oxygen drifting through empty space. At this point, the universe will enter what cosmologists call the degenerate era, named after the degenerate matter that makes up white dwarfs and neutron stars. The cosmos will be cold, dark, and seemingly lifeless, illuminated only by the occasional flash of a white dwarf collision or the brilliant but brief flare of matter falling into a black hole. But the story doesn't end there. Even in this apparently dead universe, evolution will continue, just at an almost inconceivably slow pace. The remaining matter, white dwarfs, neutron stars, brown dwarfs, planets, and rocky debris will gradually reorganize itself through gravitational interactions. Over periods of roughly 10⁻⁰ to 10⁻⁻20 years, close encounters and gravitational perturbations will either eject most objects from their galaxies entirely or cause them to spiral into the central supermassive black holes. The universe will become a collection of isolated black holes and scattered cold objects drifting through empty space. This process of gravitational evolution will be incredibly slow. To see significant changes in the structure of a galaxy, you would need to wait periods of time that are longer than the current age of the universe by factors of millions or billions. But given enough time, and time is the one thing the universe has in seemingly unlimited supply, even the most stable configurations will eventually decay. During this era, black holes will begin to dominate the universe's inventory of matter and energy. Every time a white dwarf or neutron star falls into a supermassive black hole, the black hole grows slightly more massive. Every time two black holes merge, they create a single, larger black hole. Gradually, inexorably, more and more of the universe's matter becomes locked up in these gravitational prisons. But even this slow consumption of matter by black holes pales in comparison to the next phase transition in the universe's evolution. According to some theories of particle physics, protons themselves, the building blocks of all ordinary matter, are not perfectly stable. They may decay with a half-life of roughly 10 hours and 34 years. If proton decay occurs, then in about 10 nets 34 to 10 nets 40 years, all the atoms in the universe will spontaneously disintegrate. White dwarfs will dissolve into clouds of electrons, positrons, and photons. Neutron stars will evaporate away to nothing. Even the rocky cores of long-dead planets will crumble into elementary particles and radiation. This would mark the end of the degenerate era and the beginning of what cosmologists call the black hole era. During this phase, which could last from 10 Sed 40 to 10 nets 100 years, black holes will be essentially the only organized structures left in the universe. Everything else will have either fallen into them or decayed away to individual particles dispersed across enormous volumes of space. But black holes will not be immune to the universal tendency toward decay. As we learned earlier, Stephen Hawking showed that even black holes evaporate, albeit incredibly slowly. During the black hole era, this Hawking radiation will be the primary source of energy in the universe. The evaporation process is extraordinarily slow for the black holes that exist today. A black hole with the mass of our Sun would take roughly 10⁻�67 years to evaporate completely, a period so vast that it's almost meaningless to contemplate. To put this in perspective, if the entire history of the universe so far were compressed into a single second, the evaporation of a solar mass black hole would take longer than the age of the universe. Supermassive black holes take even longer. The black hole at the center of our galaxy, with its 4 million solar masses, would take roughly 10,887 years to evaporate. The most massive black holes we know of, weighing billions of solar masses, would persist for 10⁻⁰ years or more. But eventually, even these cosmic giants will succumb to Hawking radiation. As each black hole evaporates, it will grow hotter and radiate faster, leading to a runaway process that ends with the black hole exploding in a final burst of energy. One by one, every black hole in the universe will evaporate away, leaving behind only elementary particles, photons, and gravitational waves dispersed across space. This brings us to the final era in the universe's evolution, the Dark Era, which begins around 10 to 100 years after the Big Bang and continues indefinitely. During this era, the universe will be a cold, dark, nearly empty expanse containing only a thin soup of elementary particles, photons, and perhaps some exotic forms of matter we haven't discovered yet. The temperature of the universe during the dark era will be incredibly close to absolute zero, perhaps 10⁻30 Kelvin or colder. The density will be unimaginably low, with typical distances between particles measured in light years or more. For all practical purposes, the universe will be empty. But even in this seemingly dead universe, some processes will still continue. Virtual particles will still fluctuate in and out of existence in the quantum vacuum. Occasionally, these quantum fluctuations might even create organized structures through incredibly rare statistical accidents. Some physicists have speculated that random quantum fluctuations could eventually recreate complex structures, perhaps even conscious observers, given enough time. The timescales involved in such processes are so vast that they challenge comprehension. The probability of quantum fluctuations randomly assembling even a simple molecule is astronomically small. The probability of creating a human brain through random fluctuations is so infinitesimally tiny that it would require periods of time measured not in years but in numbers so large they dwarf even the evaporation time of supermassive black holes. Yet some theories suggest that these quantum resurrections are not just possible but inevitable, given infinite time. This leads to the mind-bending possibility that consciousness itself might be eternal, flickering in and out of existence through random quantum events across the vast emptiness of the far future universe. But there are other possibilities for the universe's ultimate fate. If dark energy continues to accelerate the expansion of the universe, then eventually the expansion rate might become so extreme that it overcomes even the strong nuclear force that holds atomic nuclei together. This scenario, called the Big Rip, would tear apart every structure in the universe, from galaxy clusters down to individual atoms, in a final cosmic catastrophe. Alternatively, if dark energy is not constant, but instead changes over time, the universe's expansion might eventually slow down and reverse. This could lead to a big crunch, where all the matter and energy in the universe collapses back into a single point, perhaps triggering a new Big Bang and starting the cosmic cycle all over again. Some theories even suggest that our universe might be part of an infinite multiverse, where new universes are constantly being created through various mechanisms. Black holes themselves might serve as cosmic wombs, with every black hole giving birth to a new universe on the other side of its event horizon. If this is true, then the black holes we've been studying might be creating countless new realities, each with its own physical laws and evolutionary trajectory. But regardless of which scenario ultimately plays out, one thing is clear: black holes will play a central role in determining the universe's fate. They are the universe's most efficient energy extractors, capable of converting matter into energy with an efficiency that no other known process can match. They are the cosmos's ultimate information processors, encoding the history of everything that falls into them. And they may be the bridges that connect our universe to others, serving as cosmic gateways to realms we can barely imagine. The study of black holes has also revealed profound truths about the nature of time itself. Near black holes, time becomes relative in the most extreme way possible. The evaporation of black holes represents a kind of ultimate clock for the universe, marking the transition between cosmic eras on timescales that dwarf all other natural processes. In a sense, black holes are the universe's way of remembering its past while preparing for its future. Every black hole contains within its event horizon the entire history of everything that ever fell into it. When these black holes finally evaporate, they release this information back into the universe in the form of Hawking radiation, perhaps preserving the memory of cosmic history in ways we don't yet understand. The realization that black holes will dominate the universe's far future has profound implications for how we think about our place in the cosmic order. We live during a brief, magnificent epoch when the universe is young, active, and filled with light. But this is just a fleeting moment in cosmic history, a brief summer between the long winter of the early universe and the even longer winter that lies ahead. Yet even in that far future, when the last black holes are evaporating away in the cold darkness, the information that once described our world, our lives, and our thoughts might still exist, encoded in the quantum correlations of Hawking radiation. In a very real sense, we might be immortal, not as individuals, but as information patterns that will persist until the very end of time. The study of black holes has also taught us that the universe is far more interconnected than we ever imagined. Quantum entanglement links particles across vast distances of space and time. Wormholes might connect different regions of space-time through microscopic tunnels. And the holographic principle suggests that the information content of any region of space is encoded on its boundary, meaning that the three-dimensional reality we experience might be a projection of more fundamental two-dimensional physics. These connections imply that consciousness itself might be a far more cosmic phenomenon than we typically assume. If information is the fundamental substrate of reality, and if consciousness is a particular pattern of information processing, then consciousness might be woven into the fabric of space-time itself. Some physicists have speculated that black holes might be conscious in some sense, processing information about everything that falls into them, and perhaps even experiencing something analogous to thought or memory. While these ideas are highly speculative, they illustrate how the study of black holes has pushed us to reconsider our most basic assumptions about mind, matter, and reality. As we reach the end of our journey through the mysteries of black holes, we're left with more questions than answers. What is the true nature of the black hole interior? How is information preserved during black hole evaporation? Do black holes connect to other universes? Are we living inside a black hole right now? Will consciousness survive the heat death of the universe? These questions push us to the very limits of scientific understanding and beyond. They force us to confront the possibility that reality might be far stranger, far more wonderful, and far more mysterious than we ever dared imagine. But perhaps that's the most important lesson that black holes have taught us. They've shown us that the universe is not a collection of separate objects moving through empty space, but rather a unified, interconnected system where space and time, matter and energy, information and consciousness are all aspects of a single, deeper reality. They've revealed that the cosmos is not winding down toward a boring, predictable end, but rather evolving toward a future filled with possibilities we can barely conceive. Even in the seemingly dead universe of the far future, quantum mechanics ensures that surprises are not only possible, but inevitable. And they've demonstrated that the ultimate questions about existence, questions about the nature of reality, the meaning of information, the persistence of consciousness, are not philosophical abstractions, but physical problems that can be studied, analyzed, and perhaps even solved through careful observation and theoretical investigation. As we look up at the night sky, knowing that millions of black holes lurk invisible among the stars, we're reminded that we're part of something magnificent and mysterious. We're temporary patterns of information and energy in a universe that's experimenting with every possible form of existence across timescales so vast that our entire cosmic epoch is just a fleeting moment. But in that brief moment, we've managed to discover some of the universe's deepest secrets. We've learned to detect gravitational waves, to photograph black holes, and to peer into the very heart of space-time itself. We've uncovered the quantum mechanical nature of reality and begun to understand how information, consciousness, and cosmos are interconnected. The black holes are still out there, still feeding, still growing, still evolving toward their ultimate destiny as the universe's final survivors. They remain cosmic mysteries wrapped in event horizons, information paradoxes disguised as gravitational fields, and perhaps gateways to realities beyond our current understanding. They are the universe's way of exploring the deepest questions about existence itself. And in studying them, we've become part of that exploration conscious patterns of information investigating the cosmic processes that gave birth to consciousness in the first place. In the end, that might be the most profound truth that black holes have revealed. We are not separate from the universe we study. We are the universe studying itself, conscious agents of cosmic self-discovery, temporary arrangements of matter and energy through which the cosmos has learned to contemplate its own existence. The secrets of black holes are still being revealed, one discovery at a time. But already they've shown us that reality is far more beautiful, far more mysterious, and far more wonderful than we ever dared dream. And as we continue to explore these cosmic enigmas, we continue the universe's greatest experiment, the attempt to understand itself through the minds it has created. The darkness between the stars is not empty. It's filled with invisible giants that shape the cosmos, bend space-time, and perhaps harbor the seeds of infinite new realities. They are the universe's deepest mysteries and its ultimate destinations. They are black holes, and they are waiting for us to understand them fully.